The shallow lagoon presents an illusion of absolute tranquility. From above, the water is a lens of pale, filtering light, stretching thin over a canvas of rippled sand. It is a world dictated by the slow, rhythmic breathing of the tides. Sunlight fractures and dances across the bottom, painting shifting webs of gold over patches of swaying seagrass. Small, translucent invertebrates scuttle and burrow, playing out their tiny lives in the sediment. To a wading bird or a human walking barefoot through the warm shallows, this expanse feels devoid of tension. There are no dark, looming shapes. There is no sudden thrashing in the water column. The danger here does not patrol, and it does not cast a shadow. Instead, it is woven directly into the floor of the sea itself. Beneath a gossamer veil of settled sand, an animal lies in a state of near-perfect erasure. It has sacrificed the vertical dimension entirely, opting instead to become a living continuation of the earth. This is a stingray. Its body is dorsoventrally flattened, an evolutionary masterpiece where the pectoral fins have been stretched and expanded into broad, muscular wings that sweep seamlessly into the head. This architecture allows the creature to settle into the sediment with a profile so low it barely registers as a bump. When it wishes to vanish, it does not dig a hole. It simply undulates the outer margins of its wings, a gentle, fluttering motion that lifts a cloud of sand grains into the water. As the grains fall back down, they dust the rays back, burying it in plain sight. Only two features break the illusion of the barren seafloor. First, a pair of eyes positioned at the very highest point of the animal's back, quietly monitoring the watery horizon. Second, located just behind those eyes are the spiracles. Because the ray's mouth and delicate gill slits are pressed firmly against the suffocating sand, it cannot breathe as a normal fish would. Instead, these spiracles act as intake valves, pulsing in a slow, hypnotic rhythm, drawing clean, oxygenated water from above and pumping it down over the hidden gills. The ray is a master of dynamic concealment. It does not just choose a spot and hope for the best. It constantly calibrates its depth of burial based on the intensity of the sun, the shifting temperatures of the current, and the ambient threat of predators. It is an act of balancing the need to remain entirely unseen with the need to watch the world go by. For the most part, the stingray's life is one of quiet, benthic foraging. It is a hunter, but not one of high-speed chases. Its diet consists of the hidden, armored denizens of the sand, clams, crustaceans, and small, bottom-dwelling fish. To find them, the ray relies on a sixth sense that feels almost like magic. Embedded within its skin is a network of highly sensitive electroreceptors. These microscopic pits can detect the faint, pulsing bioelectric fields generated by the muscle twitches and beating hearts of animals buried in the dark. Imagine the sensory experience of this hunt. The ray glides over the bottom, practically hovering like a submerged ghost. It cannot see what is buried beneath it, but it can feel the electric hum of life. When it detects a subtle, rhythmic signature of a hidden shrimp or a tightly closed mollusk, the ray halts. It pivots, positioning its massive disc directly over the target. Then it presses down, using its own body as a heavy, inescapable blanket to trap the prey against sand. The mouth, located entirely on the underside of the animal, goes to work. There are no needle-like fangs here. Instead, the ray is equipped with robust, flattened dental plates. With a powerful crunch, it shatters the calcium carbonate shells of its victims, extracting the soft nutrition inside and spitting out the jagged fragments. Yet, the very evolutionary adaptations that make the stingray such an effective and stealthy hunter of the seabed also create its greatest vulnerability. By lying flat and buried, the ray removes itself from the visual field of its prey, but it also places itself squarely in the path of much larger, heavier creatures. Predators like massive sharks or wading mammals, including humans, frequently traverse these shallow waters. Because the ray is essentially invisible, it cannot rely on warning displays to keep these massive threats at bay. It is an animal built for stillness, not for sustained, high-speed flight. Therefore, when the illusion of the sand fails and an immense weight comes bearing down upon it, the ray must rely on a final, devastating layer of deterrence. This deterrence is mounted near the base of its long, whip-like tail. It is a structure known as the barb, though calling it a barb hardly does justice to its biological engineering. It is a heavily modified spine, forged from dense, calcified tissue. Along its outer edges run rows of sharp, backward-pointing serrations, functioning much like the teeth of a jagged saw. But the spine is not merely a knife. It is a complex delivery system. The entire calcified blade is tightly encased within a thin, delicate integumentary sheath. Within the grooves of this sheath lie specialized tissues that manufacture and store a potent venom. It is crucial to understand the rules of engagement here. The stingray does not use this weapon to hunt. It cannot detach the spine and fire it like a dart, nor does it swim forward to spear an aggressor. The spine is a purely defensive mechanism, and it is governed by a strict, reflexive trigger. That trigger is downward pressure. When a human foot, or the heavy snout of an investigating predator, steps down onto the buried disc of the ray, the animal's escape routes are instantly pinned. Panic and physics take over. In a fraction of a second, the ray reflexively whips its tail violently upward and forward over its own back. The motion is blindingly fast and incredibly precise, designed not to kill the intruder, but to instantly dislodge the crushing weight. If that whipping tail connects with flesh, the mechanics of the sting unfold in a brutal sequence. The sharp tip of the calcified spine pierces the skin. As it drives deeper, the delicate sheath surrounding the spine tears open, rupturing the venom glands and flooding the fresh wound with toxins. As the spine is driven in, and critically, as it is violently pulled back out, the backward-facing serrations catch and tear at the surrounding muscle and tissue. This combination creates a wound that is profoundly traumatic. It is not just a puncture, and it is not just an envenomation. It is a severe mechanical laceration paired with a chemical burn. The severity of the sting is directly proportional to the force of the misstep. The heavier the weight bearing down on the ray, the deeper the spine is driven, the more tissue is mechanically shredded, and the larger the dose of venom injected into the bloodstream. The venom itself is a complex cocktail of proteins. Interestingly, these proteins are thermolabile, meaning their molecular structure begins to break down and degrade when exposed to high heat. This biological quirk is the reason why the most effective immediate first aid for a stingray injury is immersing the affected limb in water as hot as the victim can safely tolerate. The heat literally dismantles the venom's architecture. But without that intervention, the biological effects are immediate and severe. The venom induces agonizing, intense localized pain that radiates outward from the tear. The area swells dramatically, a localized inflammatory response triggered by the invasive compounds. In the wild, this searing pain serves a very specific evolutionary purpose. If a shark bites down on the back of a buried ray and receives a spine to the roof of his mouth, the overwhelming agony is usually enough to force the shark to release its grip and flee, leaving the injured ray to survive another day. It is an aggressive, chemical negotiation demanding immediate space. Despite possessing such a formidable weapon, the stingray is fundamentally a gentle and non-aggressive creature. It desires no conflict. If a diver or a wader approaches slowly, giving the animal ample warning through the vibration of their footsteps or the displacement of the water, the ray will almost always choose flight over fight. It will erupt from its sandy bed and glide gracefully away into the deeper blue, its wings undulating in a mesmerizing, fluid rhythm. The strike only occurs when this warning window is completely erased. It is a violent reaction of a startled, trapped animal that believes it is about to be crushed to death. This defensive strategy is part of an ancient and ongoing evolutionary arms race. While the venomous spine deters the vast majority of opportunistic predators, nature always finds a workaround. Certain large, specialized sharks have learned to bypass the booby-trap tail altogether. They use their snouts to violently flip the stingray over, exposing its soft, white underbelly and rendering the dorsal spine useless. The shark then bites into the unprotected ventral side. This dynamic proves that the ray's venom is not an invincible shield. It is a selective filter. It protects the ray from the careless and the curious, but it can still fall short against a highly adapted, determined specialist. The stingray's entire existence is tied to the physical environment of the shallows, heavily dictated by the sun. As an ectothermic or cold-blooded animal, the ray cannot generate its own internal body heat. It is entirely at the mercy of the surrounding water and sand. On cooler days, or when the tide brings a chill, the ray's metabolism slows to a crawl. It becomes sluggish, choosing to remain buried deep in the sediment for extended periods to conserve precious energy. But when the sun bakes the shallow lagoon, warming the water and the sand, the ray absorbs its thermal energy like a living solar panel. Its metabolism spikes, its digestive system accelerates, and it becomes an active, voracious forager, scouring the bottom for meals. This reliance on warm shallows is also why these coastal bays and lagoons frequently serve as critical nursery grounds. Pregnant females migrate into these protected waters to give birth. The juvenile rays that emerge are miniature replicas of the adults, but they are incredibly vulnerable. Their defensive spines are proportionally tiny, and their venom glands are not fully developed. For a young ray, survival depends almost entirely on the perfection of its camouflage and its ability to flee at the first sign of a shadow. As they grow, their defensive capabilities mature. The spine itself is not a permanent fixture. Much like a shark loses and replaces its teeth, a stingray will periodically shed its barb and grow a new one. This regenerative process ensures that the blade remains razor sharp and the venom delivery system functions perfectly, repairing any wear and tear incurred from surviving the harsh realities of the reef. The presence of the stingray subtly alters the behavior of everything around it. Predators that have suffered sting and survived will often change their hunting routes, learning to avoid the sandy patches where the phantom discs lie hidden. Humans, too, must adapt. Coastal communities and experienced waders learn the stingray shuffle, sliding their feet through the sand rather than taking heavy, downward steps. This simple dragging motion sends vibrations ahead, gently nudging the buried rays and giving them the precious seconds they need to flee, neutralizing the threat of surprise encounter entirely. Ultimately, the stingray is an animal defined by the synthesis of its adaptations. It is not just camouflage, and it is not just venom. It is the seamless integration of the two. It relies on a veil of sand to make itself a ghost, and it relies on a serrated, toxic dagger to enforce its boundaries when the ghost is stepped upon. It is a creature that asks only to be left alone in the warm, sunlit shallows. It does not roam the oceans looking for a fight. It simply rests, invisible and quiet, processing the bioelectric hum of the world beneath the sand. But beneath that profound stillness lies a coiled spring of mechanical force and chemical consequence, ready to remind a heavy-footed world that invisibility should never be mistaken for defenselessness. Deep within the labyrinth of a tropical reef, the architecture of survival is written in rigid lines. Calcium carbonate fortresses rise from the ocean floor, built by the slow, collective skeleton building of corals. It is a landscape defined by armor, by crushing jaws, by speed, and by the desperate need to hide. Every surface is contested ground. In this high-stakes theater, the animals that thrive tend to wear their defenses clearly. They are wrapped in thick shells, plated with heavy scales, or equipped with the muscular power to vanish into blue in a fraction of a second. Yet, moving with agonizing slowness across a jagged expanse of coral rubble, there is an anomaly. It is a creature no longer than a human thumb, yet commands the visual field. Against the muted olive greens and pale grays of the reef substrate, its body burns with saturated, impossible colors. Electric blues, incandescent oranges, and stark, tracing lines of neon white paint its flesh. It looks like a dropped jewel or an accidental stroke of artificial paint upon a natural canvas. It appears entirely out of place, seemingly fragile and overtly conspicuous. This is a sea slug, specifically a nudibranch. It has no shell into which it can retreat. It has no scales to deflect a bite. It possesses absolutely no capacity for rapid escape. To the naked eye, it is little more than a soft, exposed morsel of protein, broadcasting its exact location to every predator in the vicinity. But the nudibranch is neither a mistake of evolution nor a helpless victim waiting to be consumed. It is, in fact, one of the most sophisticated tacticians in the ocean. It is a master of biological espionage and a specialist in grand theft. It survives in a world of heavily armed predators not by manufacturing its own weapons, but by systematically appropriating the weapons of others. To understand the genius of the sea slug, one must first look at the bizarre anatomy that adorns its back. Extending upward from its soft dorsal surface are clusters of finger-like projections known as serrata. They sway gently in the tidal currents, looking like a delicate, flowing mane or the petals of a bizarre aquatic flower. These structures serve a fundamental physiological purpose. They drastically increase the animal's surface area, allowing it to absorb oxygen directly from surrounding water, functioning as external gills. Furthermore, extensions of the slug's digestive tract reach up into the core of each and every one of these cerata. But respiration and digestion are only the mundane functions of its anatomy. The true purpose of cerata is far more sinister. It begins with a highly specific choice of prey. While other grazers on a reef seek out harmless algae or soft sponges, this particular sea slug actively hunts the unapproachable. It seeks out hydrozoans and other small colonial cnidarians. To most reef inhabitants, a hydrozoan colony is a boundary. They look like innocuous, feathery plants clinging to the rocks, but they are actually animals, and they are covered in millions of microscopic, hair-trigger weapons called nematocysts. A nematocyst is essentially a biological landmine, a highly pressurized, microscopic capsule containing a coiled, venom-tipped harpoon. When a small fish or a passing invertebrate brushes against the colony, the mechanical and chemical disturbance triggers the capsules. In a fraction of a millisecond, thousands of these harpoons fire, embedding themselves into the flesh of the intruder and pumping in a paralyzing toxin. It is an incredibly effective defense system that keeps the hydrozoan colony safe from a vast majority of grazing predators. But not from the sea slug. Driven by chemical cues in the water, the nudibranch approaches the stinging thicket without a hint of hesitation. It uses specialized sensory organs on its head called rhinophores, twin, horn-like structures that constantly taste the water, reading invisible chemical trails that guide it directly to the venomous colony. The slug has poor vision, perceiving little more than light and shadow, but in a world of complex chemistry, its sense of smell provides absolute clarity. When it reaches the hydrozoan, the slug begins to feed. It deploys its radula, a ribbon-like muscular tongue lined with microscopic, chitinous teeth, functioning much like a flexible chainsaw. It rasps away at the stinging flesh, tearing the hydrozoan polyps apart and swallowing them whole. What happens next within the digestive tract of the nudibranch is nothing short of an evolutionary miracle. If any other animal would consume this tissue, the millions of ingested nematocysts would fire internally, destroying the predator's mouth, throat, and stomach. But the sea slug possesses a unique, almost incomprehensible biological hack. As the stinging cells enter its digestive system, the slug suppresses their firing mechanism. Through a complex interplay of chemical cloaking and specialized mucus, the slug convinces the microscopic harpoons that they have not been disturbed. They remain coiled. They remain pressurized. They remain fully armed and dangerous. The slug does not digest these weapons. Instead, it carefully separates the unexploded nematocysts from the rest of the hydrozoan tissue. Then, utilizing specialized ciliated tracts within its internal plumbing, it sweeps these live, stolen bombs upward, moving them out of the main digestive stomach and routing them into the narrow canals that lead up into the cerata on its back. The stolen weapons are pushed all the way to the very tips of the cerata, where they are deposited into specialized storage compartments called cnidosacs. Here, the nematocysts are aligned, packed tightly together, and pointed outward just beneath the surface of the slug's skin. This process, known as kleptocnity, fundamentally transforms the sea slug. The animal that arrived at the colony as a soft, defenseless grazer leaves as a heavily armed, living vault of borrowed ammunition. It has successfully co-opted the defense mechanism of its prey, turning the hydrozoan's ultimate weapon into its own personal armor. The slug did not have to spend a single calorie evolving a venom gland, nor did it have to invest metabolic energy in synthesizing complex toxic proteins. It simply walked into a dangerous neighborhood, stole the ammunition, and loaded it into its own turrets. Now, the brilliant, incandescent colors of the nudibranch take on a completely different meaning. They are not an accident, and they are certainly not an invitation. This phenomenon is known as aposematism, warning coloration. In the chaotic, visually noisy environment of a coral reef, bright colors can sometimes create a disruptive camouflage, breaking up the animal's outline. But to a predator with experience, those neon blues and fiery oranges scream a very clear, universal message. I am toxic. I am painful. Do not touch me. When a naive or desperately hungry predator, perhaps a young wrasse or a curious crab, ignores a visual warning and attempts to take a bite, The sea slug's stolen defenses are instantly activated. As the predator's jaws clamp down on the soft flesh of Serrata, the mechanical pressure brakes open the nida sacs. The chemical suppression is lifted. The stolen nematocysts, still perfectly viable, perceive the attack and fire in devastating synchrony. Instead of a soft meal, the predator's mouth is suddenly flooded with thousands of venom-tipped harpoons. The intense, burning pain is immediate. The attacker recoils, violently spitting out the sea slug, shaking its head to clear the stinging agony from its lips and gills. The lesson is learned rapidly, and it is rarely forgotten. The visual memory of the bright neon slug is forever paired with a sensation of searing pain. Through this painful trial and error, the entire predator community of the reef is conditioned to leave the vivid, slow-moving creatures completely alone. The nudibranch, however, is prepared even for the most aggressive attacks. If a predator manages to secure a firm grip on the Serrata before the sting takes full effect, the sea slug employs a secondary tactical retreat. Much like a lizard dropping its tail to escape a bird, the nudibranch can perform autotomy. It actively severs a connection to the grass Serrata, dropping the fleshy appendages into the mouth of the attacker, while the main body of the slug slowly crawls away. But this is no ordinary decoy. The detached Serrata are still packed with live, stolen nematocysts. As they writhe in the water or in the predator's mouth, they continue to discharge their venom, delivering a sustained, punishing sting long after the slug has made its exit. It is a brilliant, sacrificial defense that leaves the attacker dealing with a mouthful of active grenades while the thief slips quietly back into the shadows of the reef, ready to regrow its lost appendages and steal more weapons tomorrow. This incredible strategy heavily influences the broader ecology of the coral reef. By specifically targeting and consuming stinging hydrozoans, these sea slugs act as crucial regulators of the benthic environment. Hydrozoans are aggressive space competitors. If left unchecked, their stinging colonies can rapidly overgrow the substrate, preventing young coral polyps from settling and threatening the overall diversity of the reef. The nudibranch, armed with its unique immunity and insatiable appetite, keeps these colonies in check. It crops the dangerous thickets, clearing space and maintaining the delicate competitive balance of the ecosystem. The thief is also a gardener, reshaping the underwater landscape simply by seeking out its next armory. The pace of this entire existence is governed by the sun. As ectothermic animals, sea slugs are entirely at the mercy of the water's temperature. They possess no internal furnace to keep their metabolism running. When the shallow waters of the lagoon are baked by the tropical sun, the nudibranch operates at peak efficiency. Its digestion quickens. The complex transport of stolen weapons accelerates, and it crawls across the rubble with increased determination. But as the ocean cools or when winter currents sweep across the reef, the slug's entire biology slows down. Its movements become lethargic, its feeding rate drops, and it relies even more heavily on its stored, stolen deterrents to survive the sluggish days. Its life is a constant physiological negotiation with the ambient heat of the sea. Even the reproductive life of the sea slug is a masterpiece of efficiency and bizarre biology. In a vast, sprawling ocean where finding a mate of the exact same species can be incredibly difficult for a slow-moving, nearly blind creature, evolution has provided a highly practical solution. Most nudibranch are simultaneous hermaphrodites. Every single individual possesses fully functional male and female reproductive organs at the same time. When two sea slugs finally cross paths, guided toward each other by subtle chemical pheromones trailing the current, there is no need to worry about finding the opposite sex. Every encounter is a guaranteed match. They align themselves side by side, facing opposite directions, and engage in a delicate, reciprocal exchange of genetic material. They fertilize each other simultaneously, doubling the reproductive output of the encounter. Following the mating dance, the slug seeks out a highly strategic location to leave its legacy. It does not scatter its eggs randomly into the unforgiving open ocean. Instead, using its chemical senses, it locates the very same stinging hydrozoan colonies that it uses for food and defense. It carefully extrudes its eggs, laying them down in beautiful, complex, spiraling ribbons that look like delicate lace glued to the rock. By placing its offspring directly adjacent to the venomous hydrozoans, the parent ensures two things. First, The eggs are afforded a degree of protection, as most predators will avoid the stinging colony. Second, when the microscopic, newly hatched slugs emerge in their casings, they will not have to travel far to find their very first meal. They will step out of their eggs and immediately begin the ancestral tradition, rasping away at the stinging flesh, stealing their first weapons, and continuing the cycle of chemical appropriation. To observe a sea slug moving across the reef is to watch a living contradiction. It is an animal with no natural armor, no speed, and no innate venom, parading through a gauntlet of lethal predators wearing colors that demand absolute attention. It survives not by being the strongest or the fastest, but by understanding the chemistry of an environment so intimately that it can turn the defenses of others into its own impenetrable shield. It drifts over the coral like a neon phantom, utterly unbothered by the violence that surrounds it. The reef is a marketplace of survival, a constant exchange of energy, predator, and prey. But the nudibranch refuses to play by the standard rules. It has hacked the system. It walks boldly to the firing line, wrapped in a stolen armory, a tiny, brilliant testament to the idea that sometimes the ultimate defense is simply having the audacity to steal the weapons of your enemies. Where the coral shelf fractures and plunges into the deep, indigo void, the reef wall becomes a vertical labyrinth. It is a sheer cliff face composed of ancient, calcified skeletons, deeply pitted with dark fissures, narrow chimneys, and lightless caves. In this twilight zone of the reef, the geometry of survival is incredibly complex. To navigate it requires either the rigid, armored maneuverability of crustacean or the absolute negation of solid form. From deep within a crack no wider than a human wrist, a creature begins to unspool. It does not emerge, it pours. It spills over the lip of the limestone like a heavy, viscous liquid defying gravity. There is no skeleton to limit its passage, no rigid architecture, bone or shell to dictate its shape. This is the octopus. As it pulls the entirety of its soft, bulbous mantle out into the open water, its physical identity is already shifting. It is a master of total, instantaneous transformation. In the span of a single heartbeat, the animal ceases to look like a cephalopod and becomes a seamless continuation of the reef wall. This is not the passive, incidental camouflage of a fish whose scales happen to match the sand. This is an active, neurologically driven illusion. Millions of specialized pigment sacs beneath its skin, known as chromatophores, expand and contract under direct muscular control, painting the animal's flesh in real time. Mottled browns bleed into speckled, ashen grays. A sudden flash of dark olive mimics the shadow of a passing wave, but color is only half the deception. A network of muscular hydrostats in the skin, called papillae, violently erect and manipulate the animal's texture. The once smooth flesh abruptly puckers and rises, forming ragged spikes and granular bumps that perfectly replicate the encrusting algae and porous rock. The octopus does not merely blend in, it becomes a stone. From this central, shape-shifting mass extend 8 prehensile arms. They unfurl in slow, deliberate, exploratory arcs. They do not paddle or thrust. They glide over the substrate, probing the topography of the reef with terrifying precision. To understand the octopus is to understand that its brain is not entirely confined to its head. This is an animal with a deeply decentralized nervous system. 2/3 of its neurons are distributed throughout its limbs. Each arm is, in essence, a semi-independent cognitive entity, capable of sensing, processing, and reacting to its environment without waiting for direct commands from the central brain. Along the ventral surface of each arm run hundreds of circular suction cups. These are not simple mechanical plungers. They are highly sophisticated sensory instruments. As the octopus moves, every single sucker is independently gripping, tasting, and analyzing the water and the rock. They detect the faintest chemical trails left behind by passing prey, decoding the molecular signature of crab or snail hidden deep within a lightless hole. The octopus tastes the world by touching it. When one of the exploratory arms slips into a narrow crevice and encounters a rigid, calcified shell of a crab, the dynamic of the hunt fundamentally shifts. The octopus does not launch into a violent, thrashing pursuit. It halts. It assesses the geometry of the hole and the resistance of the prey. A crab is heavily armored and equipped with powerful, crushing pincers. The octopus, conversely, is composed entirely of soft, delicate tissue. A single, well-placed pinch from a desperate crab could sever a nerve, tear open a mantle, or permanently blind a cephalopod. For the octopus, brute force is an unacceptable risk. A wrestling match is a failure strategy. Instead of overpowering the crab, the octopus relies on a weapon of absolute surgical precision. Hidden at the exact center of the webbing where the 8 arms converge lies the only hard structure in the animal's body, a sharp chitinous beak, shaped remarkably like that of a parrot. Once the arms have secured the crab, pinning its dangerous claws against its own shell, the octopus pulls the prey inward, pressing the beak against the vulnerable, articulated joints of the crab's exoskeleton. With a controlled bite, the octopus pierces the soft membrane and delivers its payload. This is a highly specialized venom containing potent neurotoxins. The injection is not designed to dissolve tissue or cause catastrophic internal bleeding. Its purpose is far more elegant: neurological sabotage. The venom immediately targets the crab's nervous system, interfering with the transmission of electrical signals across the synapses. Within moments, the crab's frantic struggling begins to slow. Its muscular coordination collapses. A profound, systemic weakness washes over it, rendering its formidable claws utterly useless. This use of venom is the ultimate expression of risk management. By pacifying the prey from the inside out, the octopus completely neutralizes the threat of retaliation. It does not need to endure a dangerous, prolonged struggle. It simply holds the crab in a dark, quiet embrace until the chemistry does the heavy lifting. Once the prey is thoroughly immobilized, the beak can go to work methodically dismantling the shell, extracting the nutrient-rich flesh while the arms maintain a flawless, unyielding grip. This biochemical mastery extends the prey that present an entirely different kind of challenge. Consider the bivalve, a clam, or a mussel. These creatures do not fight back with claws, but they possess a defense mechanism of sheer, unyielding endurance. When threatened, they slam their heavily calcified shells shut, locked together by incredibly powerful adductor muscles. To pry a clam open through sheer physical force will require an immense expenditure of calories, burning through the octopus's energy reserves. The octopus approaches the bivalve not as a physical obstacle, but as a puzzle to be dismantled. It wraps its arms around the shell, sensing the microscopic seams and the structural integrity of the calcium carbonate. If it cannot easily pry the two halves apart, it employs a specialized anatomical tool. Just inside the beak lies a radula, a rough, ribbon-like tongue covered in microscopic, abrasive teeth. The octopus presses its mouth against the shell and begins to drill. It is a slow, agonizingly patient process. The radula rasps away at the rigid armor, grain by microscopic grain, creating a tiny, perfectly circular borehole straight through the shell. The moment the drill breaks through into the interior cavity, the octopus injects its neurotoxic venom directly into the clam seal fortress. The result is inevitable. The venom washes over clam's internal tissues, specifically targeting the stubborn adductor muscle that holds the shell shut. The muscle fibers undergo localized paralysis. The tension fails. The shell slowly gapes open, a fortress conquered not by overwhelming siege engines, but by a microscopic chemical key. The octopus slips its beak inside and consumes the soft tissues. It is a triumph of persuasion over power. But the octopus is not the undisputed sovereign of the reef. It occupies a perilous middle ground in the food web. For all its intelligence and venomous capability, its soft body makes it a highly prized meal for the apex predators of the coral matrix. Massive groupers with cavernous mouths search the shadows for the outline of a mantle. Fierce moray eels, specialized for hunting in the same narrow crevices the octopus calls home, track the cephalopod by scent. When the primary defense of camouflage fails, when the illusion is broken and a predator locks eyes with the octopus, the animal must transition instantly from stealth to evasion. As the moray eel lunges, jaws snapping forward, the octopus aggressively contracts its muscular mantle. This forces a massive jet of water out through its siphon, propelling the animal backward with astonishing, explosive speed. Simultaneously, it triggers its most famous defensive mechanism. From an internal ink sac, it ejects a dense, billowing cloud of dark melanin and mucus. But this ink is far more than a simple visual smokescreen. It is a physical and chemical decoy. The mucus binds the ink together, causing it to hold the shape of a dark, floating phantom in the water, a decoy that the predator often attacks by mistake. Furthermore, the ink contains chemical compounds, such as tyrosinase, which actively irritate the predator's eyes and temporarily overwhelm its olfactory senses. The moray eel is left biting at a ghost, its vision obscured and its sense of smell deadened, while the octopus compresses its boneless body and vanishes into a crevice too small for the eel to follow. The intelligence that governs these split-second decisions is the most terrifying and fascinating aspect of the animal. The octopus is not a creature driven solely by hardwired instinct. It is a problem solver. It possesses a spatial memory that allows it to map the complex topography of its territory. It remembers which crevices harbor the most crabs, and it remembers the exact patrol routes of the local groupers. This cognitive depth manifests in chillingly calculated hunting behaviors. When an octopus discovers a crab hiding in a porous section of coral with multiple exit holes, it does not immediately charge in. It recognizes the geometry of escape. Before making its presence known, the octopus will silently extend its long arms, threading them around the coral block to plug the alternative exits. Only when the trap is fully sealed does it flush the crab from its primary hole, driving the prey directly into its waiting embrace. It is hunting with foresight. It is manipulating the battlefield. In certain tidal pools and shallow reef flats, this intelligence crosses a threshold into actual tool use. Octopuses have been observed gathering empty coconut shells or large bivalve shells, carrying them across the barren sand like mobile armor. When a threat appears, they pull the shells together from the inside, sealing themselves in an impenetrable makeshift fortress. They will meticulously stack heavy stones and discarded shells around the entrance of their dens, building physical barricades against the intrusion of moray eels while they sleep. They engineer their environment to compensate for their biological vulnerability. While the venom of the standard reef octopus is calibrated to paralyze small crustaceans, the evolutionary potential of this chemistry reaches its terrifying apex in a much smaller cousin, the blue-ringed octopus. Inhabiting the shallow tide pools and coral rubble of the Indo-Pacific, this animal is barely the size of a golf ball, yet it carries one of the most devastating chemical payloads on the planet. Unlike the cryptic, blending nature of its larger relatives, the blue-ringed octopus uses its chromatophores for a stark, lethal warning. When agitated, its pale body flares bright yellow, and dozens of iridescent, neon blue rings pulse across its skin. It is a brilliant, undeniable alarm. The venom it possesses does not merely pacify crabs. It contains tetrodotoxin, a molecule synthesized by symbiotic bacteria living within the animal's salivary glands. Tetrodotoxin is a neurological wrecking ball. It completely blocks sodium channels in the nerve cells of vertebrates, including humans. A single, relatively painless bite from this tiny octopus delivers enough toxin to cause catastrophic systemic paralysis. The victim remains entirely conscious, their brain functioning perfectly. As their voluntary muscles shut down one by one, the lungs cease to expand. The diaphragm freezes. It is a suffocating, locked-in paralysis orchestrated by a creature small enough to sit in the palm of a hand. The blue-ringed octopus proves that in the toxic food web, physical size is utterly irrelevant when matched against superior biochemistry. The physiology of the octopus, whether harmless or deadly, is tightly constrained by the physical properties of the ocean itself. They are ectothermic animals, inextricably linked to the ambient temperature of the water, but their relationship with heat and oxygen is uniquely fragile due to the very nature of their blood. Vertebrates, like fish and humans, rely on iron-based hemoglobin to transport oxygen through their veins, giving blood its red color. The octopus, however, relies on a copper-based protein called hemocyanin, which courses through its body in a spectral, ghostly blue. Hemocyanin is highly efficient in the cold, high-pressure environments of the deep ocean, but becomes a severe liability in the warm, sun-baked shallows of a tropical reef. As water temperatures rise, the ocean holds less dissolved oxygen, and simultaneously, the blue blood of the octopus loses its ability to bind and transport whatever oxygen remains. When the lagoon heats up, the octopus begins to suffocate from the inside. Its metabolism races, demanding more oxygen just as its blood fails to deliver it. This physiological crisis dictates its behavior. It forces the octopus to retreat into the deep, shaded recesses of the reef, avoiding the sun, panting heavily as it pumps water over its gills in a desperate bid to stave off hypoxia. It is a prisoner of its own alien biology, forever tethered to the cold, dark currents. The life cycle of this brilliant, venomous architect is violently brief. For all its cognitive power, an octopus lives fast and dies young, often surviving for only 1 to 2 years. Its entire existence is a rapid accumulation of knowledge and calories, all building toward a single terminal event: reproduction. For the female octopus, mating is a death sentence. Once she receives the spermatophores from a male, she seeks out the deepest, most secure cavern she can find. She crawls inside and meticulously barricades the entrance with rocks and rubble, sealing herself in the dark. She lays tens of thousands of translucent, teardrop-shaped eggs, weaving them into hanging braids as she attaches to the ceiling of her tomb. From that moment on, she ceases to be a hunter. She refuses to eat. Her entire existence narrows down to the care of those eggs. For weeks, sometimes months, she gently caresses the hanging strings with her arms, keeping them free of algae and parasites. She blows gentle currents of water from her siphon over the clutch, ensuring the developing embryos receive a constant supply of oxygen. As the eggs grow, the mother slowly consumes herself. Her body begins to undergo programmed senescence, a rapid, terrifying cellular degeneration. She loses her ability to change color. Her skin pales in tears. She becomes a ghost, blindly, mechanically tending to the future, while her own body breaks down into nothing. The intelligence, the spatial memory, the calculated hunting strategies, all of it fades as she starves. Finally, the eggs begin to hatch. Thousands of microscopic, perfectly formed octopuses erupt from the casings, drifting out of the den and up into the planktonic currents. They are born utterly alone, armed with nothing but inherited instinct and the microscopic beginnings of venom glands. As the last of her offspring drift away into the blue, the mother takes her final, shuddering breath and dies on the floor of her den, a hollowed-out husk. The reef continues its relentless rhythm. The crabs emerge from their holes. The moray eels prowl the shadows. And somewhere in the vast, drifting plankton, a new generation of soft-bodied tacticians begins to grow. They will return to the limestone walls. They will learn the geometry of the crevices. They will blend into the stone, and they will wait, armed with the quiet, devastating power of neurological sabotage. They are the ultimate expression of the reef's complexity, a creature that conquers a world of armor and teeth not with force, but with fluid, terrifying intellect and the patience of poison. When the architecture of the reef finally surrenders to the open ocean, the coral shelf plummets into a sheer, vertical abyss. Here, the water ceases to be a playful, dappled turquoise and deepens into an endless, heavy cobalt. The surge presses against the limestone buttresses with a slow, rhythmic weight. In this transitional zone between the bustling shallows and the pelagic void, a shadow detaches itself from the reef wall. It moves with a deliberate, majestic lack of urgency, gliding into the light. This is not a creature that darts or scurries. It swims with the profound, unshakable confidence of an animal that has absolutely no natural predators to fear. This is a Napoleon fish, or the humphead wrasse. To witness in the wild is to observe a living monolith. It is immense, possessing a bulk that dwarfs almost every other resident of the coral matrix. Its scales are as large as coins, painted in a mesmerizing, shifting gradient of deep jade, electric cyan, and pale, shimmering turquoise. The colors seem to pulse and change as the animal tilts its massive body, catching the filtered sunlight that penetrates the depths. Its face is heavy, ancient, and undeniably imposing. Above a pair of remarkably perceptive, independently rotating eyes rises a prominent, bulbous forehead, a thick, fatty dome that gives the fish its imperial namesake. Below this dome, heavy, fleshy lips protrude, framing a mouth that seems locked in a permanent, stoic frown. There's a distinct aura of antiquity surrounding the Napoleon fish. It does not behave like the frantic, fast-burning inhabitants of the upper reef. It patrols its territory with the slow, measured cadence of an absolute sovereign. And yet, beneath that serene and lumbering exterior lies an apparatus of incredible, localized destruction. The Napoleon fish is an apex consumer of the heavily armored. While other predators seek out soft-bodied fish or rely on the paralyzing effects of venom, the humphead wrasse relies on pure, unadulterated mechanical force. It feeds on the reef's most heavily fortified inhabitants, crustaceans encased in thick chitin, heavy-shelled mollusks bolted to the rock, and most notably, the bristling, needle-covered spheres of sea urchins. To a standard predator, a sea urchin is a painful impossibility. To the Napoleon fish, it is merely a wrapped parcel of calories waiting to be opened. When the wrasse locates a large urchin wedged into a coral crevice, it does not hesitate. It approaches a barricade of spines with thick, callous lips that are seemingly impervious to the sharp tips. The fish maneuvers its jaws, securing a grip on the urchin's rigid test. Then, the true biological weaponry is engaged. Deep within the throat of the Napoleon fish lies a specialized set of pharyngeal teeth. These are not the sharp, grasping teeth of a shark. They are heavy, flat, calcified grinding plates powered by immensely strong musculature. With a powerful, sickening crunch that can literally be heard echoing through the water column by passing divers, the wrasse pulverizes the urchin. The rigid calcium carbonate shell splinters and collapses inward. The wrasse grinds the armor defense into a useless, gritty paste, swallowing the nutrient-rich gonads and soft tissues within, and passing the crushed remnants of the shell through its digestive tract. This act of violent consumption is, ironically, an act of profound ecological stewardship. The Napoleon fish is a keystone engineer of the coral reef. Sea urchins are voracious grazers, scraping away at the substrate with their own specialized teeth. In moderate numbers, they keep algae in check, but without a massive predator to control their populations, urchins can rapidly overpopulate. An unchecked urchin boom acts like a plague of locusts, aggressively overgrazing the reef to the point where they strip away the essential coralline algae that baby corals need to anchor themselves, eventually eroding the very foundation of the reef itself. By routinely crushing and consuming these spiky grazers, the Napoleon fish single-handedly maintains the structural integrity of its environment. It holds a line, ensuring that the coral has the space and stability to grow. The sheer size of this fish is a testament to its mastery of time. The Napoleon fish is a creature of slow, deliberate accumulation. They are exceptionally long-lived, routinely surviving for 3 to 5 decades in the wild. This extraordinary lifespan is coupled with a fascinating, highly complex reproductive strategy known as protogynous hermaphroditism. Every single Napoleon fish begins its life as a female. For years, they roam the reef in a relatively modest size, integrating into the complex social hierarchy of the wrasse community. But time and the social dynamics of the reef trigger a spectacular transformation. As the largest, most dominant males in the territory eventually die off of old age or predation, a biological trigger is pulled within the largest remaining females. Driven by a surge of specific hormones, a female will begin to change. Her colors deepen and shift. The iconic, fatty hump on her forehead begins to swell and protrude. Her internal reproductive organs literally restructure themselves. Over the course of months, she transitions entirely into a fully functional, dominant supermale, taking over the territory and the reproductive rights of the harem. This slow, decades-long progression from juvenile to female to massive, dominant male means that the largest individuals on the reef are biological archives. They have lived through countless seasons, witnessed shifts in the ocean's temperature, and fed continuously in the exact same territory for half a century. And it is precisely this longevity, this massive size, and this unyielding apex diet that introduces a Napoleon fish to the toxic food web. The grand twist of the humphead wrasse is that it is fundamentally harmless in its biology. It has no venom glands. It does not synthesize deadly proteins. It possesses no stinging spines. And yet, this magnificent gentle giant can be one of the most chemically dangerous animals in the entire ocean. The danger does not come from within the fish. It comes from beneath it. It comes from the invisible, microscopic foundation of the very reef it protects. The phenomenon is known as seguadera, and its mechanics represent the ultimate, invisible escalation of toxicity. The story begins at a scale completely undetectable to the human eye. Clinging to the blades of turf algae and the surfaces of dead coral rubble are billions of microscopic, single-celled organisms called dinoflagellates. Under the right environmental conditions, these specific microbes manufacture a highly complex, lipid-soluble compound called ciguatoxin. At this microscopic level, the toxin is practically meaningless, but the reef is an engine of consumption. Small, herbivorous fish flutter over the rubble, scraping up the algae, and in the process, they inadvertently consume millions of these toxic dinoflagellates. The herbivore does not die. Its biology simply absorbs the ciguatoxin, storing resilient molecules within its fat, its liver, and its muscle tissue. Then, a slightly larger predatory fish darts out from the shadows and consumes the herbivore. It does not just absorb the calories. It inherits the accumulated toxin. Because ciguatoxin is remarkably stable, it does not break down easily in the digestive tract. It begins to stockpile. This process is called biomagnification. With every step up the food chain, the concentration of the poison exponentially increases. Enter the Napoleon fish. As a massive, long-lived apex predator with an incredibly diverse diet, it sits at the absolute pinnacle of this trophic pyramid. For 30, 40, or 50 years, the wrasse continuously consumes smaller predators, crustaceans, and grazers. With every single meal, a microscopic trace of ciguatoxin is deposited into its massive, muscular flanks. The fish itself is entirely immune to the effects. The neurotoxin does not slow its swimming, it does not dull its senses, and it does not shorten its lifespan. The wrasse swims to the blue as a pristine, flawless specimen of marine evolution, totally oblivious to the deadly chemical payload it carries within its own flesh. The paradox of the Napoleon fish is agonizing. To look at it is to see the absolute picture of health and vitality. Its meat is firm, white, and completely untainted by any foul odor or strange discoloration. There is absolutely no physical warning that the fish has been compromised. Yet, if a human were to catch and consume a large, older Napoleon fish from a reef experiencing a dinoflagellate bloom, the consequences would be catastrophic. Ciguatera poisoning in humans is a profound neurological nightmare. Because the toxin is completely heat-stable, no amount of cooking, boiling, or frying will neutralize it. Once ingested, the ciguatoxin rapidly binds to the voltage-gated sodium channels in human nerve and muscle cells. It forces these cellular gates to remain open, causing the nerves to continuously, uncontrollably fire. The symptoms are bizarre, terrifying, and deeply disorienting, beyond severe gastrointestinal distress and a plunging heart rate. The victim's nervous system begins to hallucinate at a tactile level. The hallmark symptom of ciguatera is temperature reversal. A person holding a cold glass of water will scream in pain, feeling as though their hand is submerged in boiling oil. A hot shower feels like shards of freezing ice. Severe joint pain, extreme muscle weakness, and an overwhelming, crushing fatigue can last for weeks, months, or in extreme cases, years, as the fat-soluble toxin stubbornly refuses to leave the human body. The Napoleon fish, therefore, acts as an unwitting biological magnifying glass. It takes a harmless, microscopic chemical whisper from the bottom of the ocean and concentrates it into a roaring, neurotoxic scream. This silent accumulation of toxicity is becoming increasingly volatile due to the changing climate of the oceans. The dinoflagellates that produce ciguatoxin thrive in disturbed environments. When human-driven climate change warms the ocean waters, or when massive storms shatter coral reefs, the resulting dead coral provides vast tracts of newly available real estate for algae to grow. As the algae bloom, the toxic dinoflagellates bloom with them, the baseline level of poison entering the food web spikes. Consequently, a Napoleon fish patrolling a degraded, warming reef will accumulate lethal doses of ciguatoxin much faster than one living in a pristine, stable ecosystem. The chemical burden of the fish is a direct, measurable reflection of the environmental stress being inflicted upon its home. Tragically, this immense toxic potential does little to protect the Napoleon fish from its greatest threat. The wrasse is highly prized in the luxury live reef fish trade, particularly in Southeast Asian markets. Its massive size, the unique alien profile of its hump, and the sheer rarity of finding a mature adult make it a status symbol. Diners will pay exorbitant sums to select a live Napoleon fish from a tank, valuing the prestige of the meal over the inherent, invisible risks of ciguatera. Because it takes decades for a female to transition into a large male, the species is incredibly vulnerable to overfishing. When the massive males are specifically targeted and pulled from a reef, the social structure collapses, the breeding aggregations fail, and the population plummets. The irony is as dark as the deep water the wrasse inhabits. Humans are hunting an endangered, ecologically vital reef guardian to the brink of extinction, fully willing to risk severe neurological poisoning simply for the privilege of consuming a giant. To encounter a Napoleon fish underwater is an experience that borders on the spiritual. They are deeply intelligent animals, displaying a level of curiosity rarely seen in wild fish. When a diver approaches the reef wall, a mature wrasse will often alter its course, gliding out of shadows to investigate the strange, bubble-blowing intruder. It does not flee. It approaches to within arm's reach, its large, swiveling eyes making direct, unmistakable contact. It assesses a human with a quiet, calculating grace, hovering effortlessly in the surge. In that moment of suspended contact, the reality of the toxic food web comes into sharp focus. Here is a creature that possesses a mechanical power to crush stone. It dictates the survival of the coral by controlling the grazers. It bends time, changing its very sex to ensure the continuation of its lineage. And yet, its ultimate danger is completely invisible, born from the microscopic organisms that coat the rocks beneath it. The Napoleon fish is not a villain of the reef, nor is it a venomous assassin. It is the grand, swimming ledger of the ocean's chemistry. It represents a profound truth that in the wild, nothing exists in isolation. The microscopic and the massive are inextricably linked through the endless cycle of consumption. The toxins of the smallest cell are inherited by the greatest giant, carried quietly upward to the decades, locked inside a beautiful, shimmering monolith drifting silently along the edge of the blue. The tide recedes, and the ocean strips away its protective depth. What remains is a skeletal landscape. The reef at low tide ceases to feel like the open sea. It becomes an exposed, unforgiving city of jagged limestone and dead coral. Water thins into warm, wavering sheets that ripple across channels of coarse sand, leaving scattered, isolated tide pools between knotted outcrops of rock. It is a terrain of shadows and sharp edges. Small fish weave anxiously through remaining crevices, and crabs test the shallow air with cautious, jerking movements. To an untrained eye, this environment appears entirely static and mineral, an uneven, lifeless scatter of rock, algae, and sediment. Yet, in the quiet depressions where the sand settles and filamentous algae wave lazily in the weak current, a form lies so perfectly integrated into the substrate that it defies the very definition of a living organism. It does not announce itself with sudden motion, nor does it broadcast its presence with a vibrant warning color so common to the toxic food web. Instead, it erases its identity entirely. This is the stonefish. To call the stonefish a master camouflage is a profound understatement. Camouflage implies a creature hiding behind its environment. The stonefish does not hide. It becomes a topography. Its body is heavily modified, resembling a fractured, eroded fragment of reef broken loose and partially buried by the tide. The skin is utterly devoid of smooth, fish-like scales. Instead, it is highly textured, covered in fleshy lobes, warts, and irregular ridges that perfectly mimic the encrusting sponges and calcified algae of the ocean floor. Its pigmentation is a chaotic, masterfully calibrated palette of mottled browns, dull olive greens, and grayish reds, reflecting the exact chemical decay of its surrounding habitat. Even the eyes, positioned high on the heavy, sloping skull, protrude only slightly. They lack the glossy, spherical prominence typical of fish, blending seamlessly into the irregular, pitted surface of the face. In many older individuals, the biomimicry extends beyond mere shape and color. Hydroids, filamentous algae, and microscopic marine organisms actually colonize and grow directly upon the stonefish's skin, cementing the illusion. The outline of the animal completely dissolves into the rubble. There is no head, no tail, no flank. There's only the continuous, unbroken architecture of the reef. This visual erasure is the first layer of a highly specialized survival strategy, and it serves a dual purpose. It is both the ultimate cloak of defense and the primary weapon of predation. The stonefish is an ambush predator of the highest order, but its method of hunting challenges our conventional understanding of the chase. In the hyper-competitive ecosystem of the coral reef, most predators expend massive amounts of caloric energy in pursuit. They rely on burst speed, prolonged chases, or the exhausting effort of outmaneuvering agile prey. The stonefish completely opts out of this energetic arms race. Its hunting philosophy is rooted in absolute immobility. A stonefish will settle into a depression in the sand, using its pectoral fins to shovel sediment over its lower half until only the jagged dorsal ridge and the top of its head remain exposed. And then it waits. It does not twitch. It does not adjust. It becomes a monument to patience. Because it is an ectothermic animal, its metabolism is tightly bound to the temperature of the surrounding water. By refusing to move, it drops its energetic demands to a barely perceptible hum. It can afford to wait for days, occasionally even weeks, for the precise moment of opportunity. That opportunity arrives when a small, unsuspecting fish or crustacean, seeking shelter from the open water, swims down toward the comforting illusion of the coral rubble. The prey hovers over the stonefish, completely unaware that the rock beneath it is breathing. When the target drifts within a precise, microscopic range, the stillness shatters. The stonefish's massive cavernous mouth, which hinges upward toward the surface, expands with explosive, terrifying violence. This action is not a bite. It is a demonstration of fluid dynamics. By throwing its jaws open and rapidly expanding its buccal cavity in a fraction of a millisecond, the stonefish creates an instant, localized vacuum. The resulting pressure differential is so powerful that the surrounding water, and anything suspended within it, is violently sucked inward. The strike happens faster than the human eye can track, and certainly faster than the prey's neurological system can process. There is no desperate chase, no flurried escape attempt, no display of speed across the open water. The hunt is decided, executed, and concluded before the prey even registers that the seafloor has opened up to swallow it. As quickly as the jaws snap shut, the stonefish settles back into its depression. The sediment slowly drifts back down. The illusion of the dead rock instantly reforms. The violence is surgically precise and entirely contained. Yet, as brilliant as this predatory strategy is, lying motionless on the bottom of a crowded, heavily trafficked reef presents an extreme biological hazard. The stonefish is heavily built, sluggish, and practically incapable of sustained swimming. If a massive grouper, a foraging shark, or a heavy-footed terrestrial mammal were to investigate or trample the irregular shape, the stonefish could not simply dart away. Its camouflage delays detection, but when concealment inevitably fails, the animal requires a secondary mechanism of survival. It is here that the stonefish transitions from a passive ambush predator into one of the most mechanically devastating organisms on the planet. Hidden along the ridge of its back, buried beneath the fleshy, algae-covered lobes of skin, lie 13 stout, heavily reinforced dorsal spines. These spines look like broken shards of thick, calcified coral. They are not positioned for active stabbing. The stonefish cannot rear back and strike like a snake, nor can it whip its tail like a ray. The spines are entirely reactionary. They are the core components of a pressure-triggered biological syringe system, primed exclusively for retaliation. At the base of each rigid spine lies a pair of highly developed venom glands. The spine itself is grooved, functioning as a hollow needle, and is encased in a protective integumentary sheath. The genius of this system lies in its mechanical trigger. A predator swimming by and lightly brushing against the stonefish's back will not necessarily trigger a catastrophic injection. The system requires downward force. When a heavy weight, such as a descending jaw of a shark or the full body mass of a human foot, compresses a dorsal ridge, the physics of the sting engage. The downward pressure pushes the fleshy sheath down along the shaft of the spine, exposing the needle-sharp tip. As the weight continues to press down, the venom glands at the base are violently squeezed. The venom is forced upward to the grooves of the spine and injected directly, deeply, into the tissues of whatever is applied the pressure. This creates a terrifying mathematical reality. The venom delivery is a force multiplier. The heavier the object stepping on the stonefish, the deeper the thick spines penetrate. The spines are remarkably robust, capable of easily piercing the tough, cartilaginous mouths of large predators or punching straight through the thick rubber soles of human footwear. The deeper the penetration, the more venom is forcefully evacuated from the glands into the wound. The stonefish essentially weaponizes the attacker's own body weight against them. The venom itself is a highly complex, devastating biochemical cocktail. It contains a specialized protein called stonefish, which operates as a multi-system wrecking ball. Upon injection, the toxin immediately attacks the cellular membranes of the victim, causing massive, localized cell death and tissue necrosis. But the true horror of the venom lies in its interaction with cardiovascular and neuromuscular systems. In smaller predators, the envenomation triggers catastrophic physiological collapse. But in humans and larger mammals, the hallmark of the stonefish sting is pain. It is not merely a sharp ache or a burning sting. It is widely documented by medical professionals and survivors as one of the most excruciatingly intense pains known to human experience. The agony is immediate, radiating outward from a puncture wound with blinding intensity, often described as feeling as though the limb has been plunged into a furnace while being crushed in a vice. This disproportionate level of pain is not an accident in biology. It is a highly refined evolutionary deterrent. The stonefish does not want to kill the creature that stepped on it. It wants the creature to instantly, violently remove its weight. For a shark or a massive ray attempting to swallow the fish whole, the sudden explosion of searing agony in the roof of the mouth forces an immediate regurgitation. The cost of the meal becomes instantaneously, prohibitively high. Systemic effects rapidly follow the pain. Depending on the depth of the puncture and the number of spines engaged, the venom causes severe swelling, rapid drops in blood pressure, respiratory distress, and, without medical intervention, potential heart failure. Yet, despite this lethal capability, the stonefish is fundamentally a pacifist in its behavior. It is not aggressive. It does not actively pursue divers, nor does it launch unprovoked defensive strikes. In controlled observations, stonefish will allow a diver to approach within inches, remaining absolutely motionless, trusting completely in its camouflage to the very last possible second. The spines remain safely sheathed unless mechanical compression demand their use. This deep passivity underscores the profound evolutionary logic of the venom system. Synthesizing complex proteins like stonefish requires a significant metabolic investment. For a fish that relies on saving energy to survive long periods between meals, wasting venom in a panic is ecologically irresponsible. The toxin is an insurance policy against catastrophic predation or accidental trampling, to be cashed in only when physical contact is unavoidable. The presence of the stonefish exerts a quiet, invisible pressure on the psychology of the reef ecosystem. The reef is not just a physical structure. It is a landscape of learned behaviors. Fish species that share evolutionary history with the stonefish navigate the rubble fields with extreme caution. They hover slightly higher above the substrate, carefully evaluating irregular surfaces before settling down to rest. Certain specialized crustaceans and smaller predators seem to recognize the subtle, unnatural contours of a buried stonefish and actively alter their foraging paths to maintain a respectful distance. This interaction suggests a constant, silent arms race. Camouflage, no matter how flawless, is never completely infallible. Over millions of years, prey species slowly evolve better visual acuity, learning to detect minute deviations in shadow or texture. In response, the stonefish maintains a remarkable morphological plasticity. No two stonefish look exactly alike. Some are covered in long, filamentous weed-like growths. Others are smooth and encrusted like dead coral. This extreme physical variation prevents predators and prey from forming a single, reliable search image in their minds, ensuring the illusion remains unbroken. The life cycle of the stonefish further highlights this balance between vulnerability and defense. A juvenile stonefish faces immense challenges. Before its body has fully developed the complex, warty textures necessary for perfect camouflage, and before its venom glands have matured to their peak lethal potency, it is highly susceptible to predation. During these early stages, the mortality rate is staggering. This intense pressure selects aggressively for rapid growth and the swift development of the dorsal spine defenses. A young fish that cannot perfectly resemble a rock must rely far more heavily on the chemical deterrent of its spines. As it matures, thickens, and its camouflage improves, the reliance shifts subtly back toward invisibility, though the venom remains fully loaded, perpetually waiting in the dark. Within the broader architecture of the toxic food web, the stonefish occupies a very specific defensive apex. It does not drift aimlessly through the water column, dragging a net of stinging cells like a jellyfish. It does not advertise its toxicity with brilliant neon warnings like a sea slug. It does not actively hunt with venom like an octopus. Instead, the stonefish operates under a philosophy of absolute integration and uncompromising retaliation. It blends so deeply into the foundation of the ocean that it ceases to be an animal and becomes an environmental hazard. The reef floor becomes safer for the stonefish precisely because the very act of touching it carries such devastating consequences. Observing a stonefish in its natural habitat profoundly challenges our assumptions about how danger operates in the wild. It lies entirely inert. It is a breathing stone, its presence betrayed only by the faintest flutter of a gill cover or the subtle shifting of its eyes tracking a passing shadow. A small, silvery fish drifts too close to the rubble, seeking shelter from the current. A vacuum opens. The prey vanishes. Minutes pass, and the absolute calm of the seafloor resumes. A massive stingray glides silently overhead, its shadow passing over the jagged dorsal ridge, careful not to press its heavy disc downward onto the uneven terrain. The stonefish remains unchanged. Its 13 spines are sheathed. Its venom glands are undisturbed. The true, terrifying hazard of this animal emerges only when the rules of the reef are broken, when the weight descends, when the camouflage is breached, and when the illusion of the rock is crushed. In that single violent instant, the quiet substrate transforms into a concealed biochemical defense system. The spines depress, the venom flows, and the cost of misstep is imposed with surgical, mechanical precision. There is no roar of a predator, no frantic chase, no thrashing struggle. There is only the silent, mechanical response of a pressure-triggered syringe embedded within living stone. It is a masterclass in survival, invisibility shaping the battlefield, and chemical agony standing as the final, absolute barrier. In stillness, the stonefish survives. Under pressure, it destroys. At the vanguard of the reef, where the jagged coral architecture intercepts the relentless push of the open ocean, a garden appears to bloom, anchored to the sunlit crests and the edges of tidal channels. Clusters of soft, undulating forms sway in perfect synchrony with the surge. They are crowned with rings of delicate, trailing filaments that catch the morning light, radiating soft hues of violet, neon green, and pale rose. To the human eye, they mimic the gentle, terrestrial beauty of a blooming flower. Even their name, the Sea Anemone, is borrowed from a terrestrial blossom. But this aesthetic grace is a profound biological deception. The sea anemone is not a plant, and it is certainly not a passive ornament. It is a carnivorous, muscular predator. It is a creature that has completely abandoned the concept of the chase, choosing instead to weaponize stillness. It has engineered a way to let the rhythmic, kinetic energy of the ocean do its hunting. The anatomy of the sea anemone is a marvel of sedentary efficiency. Its foundation is a thick, highly muscular column that ends in a specialized adhesive pad called a basal disc. This disc secretes a powerful biological cement, gripping the pitted limestone of the reef with such incredible tenacity that even the violent, tearing force of a tropical storm surge struggles to dislodge it. From this immovable base rises a column, topped by an oral disc that houses a central, slit-like mouth. Framing this mouth is the anemone's defining feature and its ultimate weapon, a dense canopy of tentacles. These tentacles do not actively search the water. They do not reach out to grab passing prey. They simply extend and hold their ground. The anemone deliberately positions itself in the high-traffic corridors of the reef, the bottleneck channels and exposed crests where tides and currents funnel a constant, reliable stream of plankton, drifting invertebrates, and small, exhausted fish. The ocean becomes a perpetual conveyor belt, blindly delivering meals directly into the anemone's waiting canopy. To understand the lethality of this waiting game, one must examine the microscopic surface of a single tentacle. It is not merely a physical barrier. It is heavily armed. Packed by the millions along the outer epidermal layer are specialized, explosive cells called nematocysts, shared across the evolutionary lineage of all cnidarians. These cells are microscopic, pressurized capsules containing highly coiled, hollow, venom-tipped harpoons. They are armed with hair-like sensory triggers that constantly read the water. When a small, erratic reef fish, fighting against the current, accidentally grazes a soft, inviting edge of a tentacle, the response is not a conscious decision by the anemone. It is a mechanical, instantaneous detonation. In a fraction of a millisecond, thousands of these microscopic harpoons fire simultaneously. They shatter the cellular membranes of the fish, burying themselves deep into its muscle tissue and instantly pumping a payload of complex neurotoxins. The immediate physiological effect on the prey is catastrophic. The neurotoxins are specifically calibrated to violently disrupt the communication between nerve and muscle. The fish experiences rapid, uncontrollable spasms followed almost immediately by profound paralysis. But the sea anemone does not rely on venom alone. If it were merely a stinging organism like a drifting jellyfish, a swift fish might endure the initial shock and thrash its way free of the tentacles before the paralysis could fully set in. The anemone prevents this escape through a secondary, often overlooked mechanism. The tentacles are incredibly adhesive. They secrete a thick, specialized mucus that functions as a biological glue. The sea anemone is, in reality, a living venomous glue trap. When the stunned fish reflexively violently thrashes to pull away from the burning pain, it only seals its own doom. The thrashing motion drives the fish deeper into the canopy. The sticky mucus grips the prey's scales, and the physical struggle triggers tens of thousands of additional nematocysts on adjacent tentacles to fire. The more the victim fights, the more tightly it is held, and the heavier the dose of paralyzing neurotoxin it receives. The struggle is brief, frantic, and entirely futile. Once the prey is completely immobilized, the anemone's decentralized nervous system orchestrates the next phase. Lacking a central brain, the anemone operates on a diffuse nerve net, a web of sensory neurons that allows the entire organism to react in coordinated harmony. The tentacles that have secured the prey begin to contract and curl inward. Slowly, methodically, they fold the paralyzed fish toward the center of the oral disc. The slit-like mouth expands, stretching wide to accommodate the meal, and the fish is pulled down into the dark, internal hollow of the gastrovascular cavity. Here, in this sealed biological chamber, the digestion process begins. The anemone floods the cavity with powerful, dissolving enzymes, breaking down the proteins and tissues of the fish externally before the nutrients are absorbed into the anemone's own cellular walls. This process can take days, because the anemone expends virtually no caloric energy swimming or chasing prey. Its metabolic overhead is astonishingly low. It can survive on irregular, sporadic deliveries from the current, hoarding energy when the water is rich with life, and slowing its metabolism to a crawl when the current runs empty. This static, heavily fortified existence exerts a massive, invisible influence over the spatial dynamics of the entire reef. The presence of a large sea anemone or a dense cluster of them fundamentally alters the swimming patterns of the surrounding community. Small grazing fish and wandering crustaceans learn to recognize the swaying tentacles as a hard, lethal boundary. The anemone essentially projects a no-go zone around itself. Fish will actively alter their trajectories, swimming in wide arcs to avoid the adhesive canopy. For predators hunting in the area, the anemone becomes a navigational hazard. A snapper or a grouper engaged in a high-speed pursuit must suddenly brake and veer off if its target darts too close to the stinging fields. The risk of accidental, blinding envenomation is simply too high. By merely existing, the sea anemone bends the architecture of the hunt, dictating where the prey can flee and where the predators dare to follow. Yet, the reef is an ecosystem built on exceptions and exploited loopholes. Within this impenetrable fortress of venom and glue, a glaring anomaly exists. Darting with absolute impunity through the lethal thicket is the clownfish, brightly colored, completely devoid of heavy scales or its own venom. The clownfish treats the anemone not as a trap, but as a sanctuary. This relationship is a masterclass in biochemical negotiation. The clownfish is not born inherently immune to the anemone's sting. A juvenile clownfish must earn its safe passage. Approaching the host anemone with extreme caution, the young fish engages in a delicate dance of acclimation. It lightly grazes the very tips of the tentacles, retreating immediately when stung and returning to brush again. Over hours and days, the fish fundamentally alters the chemistry of its own external mucus coat. It either strips away the specific molecular triggers that tell the anemone to fire, or it actively incorporates the anemone's own chemical signature into its skin. Eventually, the anemone is biochemically fooled. Its hair-trigger nematocysts no longer recognize the clownfish as a foreign body or a potential meal. The fish becomes invisible to the weapon. Once this chemical cloaking is achieved, the anemone inadvertently provides the ultimate, unbreachable fortress for the small fish. Predators that would easily consume the clownfish in open water are forced to stop at the perimeter of the stinging tentacles, watching helplessly as their prey hovers securely inside the lethal canopy. But the sea anemone does not provide the security for free. The relationship is highly transactional. The clownfish acts as a frantic, aggressive housekeeper. It aggressively chases away specialized reef predators, like certain butterfly fish, that actually enjoy eating anemone tentacles. As the clownfish darts in and out of the host, its constant movement significantly increases the flow of oxygenated water deep between the tentacles, acting like a living ventilation system. Furthermore, the nitrogen-rich waste excreted by the fish is absorbed directly by the anemone, providing a constant, vital stream of fertilizer. This fertilizer feeds not just the anemone, but the microscopic, photosynthetic algae that live deep within its tissues, like the hard corals that build the reef. Many sea anemones harbor these symbiotic algae, exchanging safe harbor and nutrients for a steady supply of solar-powered sugars. This dual-income system, harvesting meat from the current and sugar from the sun, makes the sea anemone an incredibly robust survivor. However, this reliance on solar energy and ambient water temperature is also the anemone's greatest vulnerability. As an ectotherm, its biological rhythms are utterly enslaved by the climate. When the tropical sun beats down and the waters warm to a comfortable degree, the anemone thrives. Its digestive enzymes work with fierce efficiency, and its tentacles extend fully, hungry for the current. But when the ocean experiences prolonged, unnatural heat waves, the delicate symbiosis within its tissues begins to violently unravel. The microscopic algae, stressed by the soaring temperatures, become toxic to their host. The anemone is forced to expel them, spitting out its primary source of solar energy. This is the tragic phenomenon of bleaching. The vibrant, neon colors fade into a ghostly, translucent white. The anemone does not die immediately, but it is deeply weakened, forced to rely entirely on whatever prey the current delivers while slowly starving from the inside out. If conditions remain stable, however, the anemone's strategy for dominating the reef is terrifyingly effective, relying heavily on its capacity for endless replication. While they can reproduce sexually, releasing clouds of gametes into the water column to drift and settle on distant rocks, sea anemones possess a far more immediate method of conquest. They can literally tear themselves apart. Through a process of asexual reproduction known as binary fission, a single, solitary anemone will anchor two sides of its muscular base of the rock and slowly pull in opposite directions. The tissue stretches, thins, and eventually rips straight down the middle. Over the next few weeks, the two halves heal, regenerate their missing parts, and become two perfectly identical, fully functional clones. Over decades, this slow-motion cellular division can transform a single, isolated organism into a sprawling, contiguous field of identical warriors. What was once a single hazard becomes an impenetrable, sprawling minefield covering entire sections of the reef. The tentacles interlock, creating a vast, swaying carpet of venom and glue that monopolizes the substrate and locks out competing corals. The sea anemone's existence is a testament to the power of unwavering patience. It does not possess a brain, a skeleton, or eyes to see the world around it. It knows only the push and pull of the tide, the touch of a struggling fish, and the chemical scent of the water. Yet, with these simple inputs, it commands absolute respect from the most advanced, highly evolved predators of the ocean. As evening approaches and the reef transitions into its nocturnal phase, the anemone remains unchanged. Its muscular column stands rigid against the shifting tide. Its tentacles extend, glowing softly in the fading light, reading the water, waiting for the inevitable mistake. It is a creature that proves that on the coral reef, power does not always belong to the fastest, the strongest, or the most aggressive. Sometimes, absolute power belongs to the organism that simply anchors itself to the stone, arms its invisible traps, and lets the world come to it. Where the vibrant, chaotic architecture of the coral shelf abruptly ends, the ocean floor falls away into a sheer, vertical plunge. The water transitions from a sun-dappled, chaotic turquoise into a heavy, featureless expanse of deep pelagic blue. It is a boundary of profound vulnerability. For the small, schooling fish that inhabit the reef, this edge is the limit of their known universe. Beyond it lies an environment devoid of hiding places, crevices, or cover. It is a space where only speed and raw power dictate survival. Hovering exactly on this threshold, suspended in the mid-water with the chilling stillness of a drawn bowstring, is a predator stripped of all unnecessary biological extravagance. There are no flowing, venomous fins here. There is no intricate, color-shifting camouflage. There is no heavy, impenetrable armor. This is the great Barracuda. It is a creature engineered by the relentless physics of the ocean to be the ultimate biological torpedo. To look at a Barracuda is to look at a weapon forged from living silver. Its body is highly elongated and perfectly hydrodynamic, a rigid cylinder of muscle tapering to a broad, powerfully forked tail. Its flanks are plated with scales so reflective they mirror the surrounding water, making the animal appear as little more than a glint of displaced light until it's far too close. But it is the face of the Barracuda that commands absolute primal respect. The skull is sharply angular, dominated by a pronounced, jutting lower jaw. When the mouth rests slightly open to allow water to pass over its gills, it reveals rows of terrifying, interlocking canine teeth. They are not the uniform, crushing plates of a bottom feeder. They are irregular, dagger-like, and razor-sharp, designed for one singular purpose: to seize, secure, and violently tear through flesh and bone in a fraction of a second. The hunting strategy of the Barracuda is a masterclass in kinetic potential. It does not actively roam the reef in a constant, exhausting search for calories. Instead, it employs a strategy of high-stakes ambush. It holds its position at the edge of the drop-off or near the surface of the water column, utilizing subtle, imperceptible twitches of its pectoral fins to remain perfectly stationary against the pushing current. Its large, highly adapted eyes are locked onto the bustling activity of the reef below and the silvery flashes of bait fish schooling in the open water above. When a target wanders too far from the safety of the coral, or a school of sardines loses its tight, defensive formation, the Barracuda engages. The transition from absolute stillness to maximum velocity is explosive. The powerful muscles running down the length of its spine contract in a massive, synchronized wave. The forked tail beats against the dense water with incredible force, propelling the rigid body forward in a terrifying surge of acceleration. In short bursts, a large Barracuda can achieve speeds that render evasion nearly impossible for a smaller fish. It overtakes the prey before the victim's lateral line can even register the displacing pressure wave of the attack. The strike is a violent collision of physics and anatomy. The Barracuda does not attempt to swallow its prey whole in a delicate vacuum like a grouper. It hits the target at full speed, its jaws snapping shut with bone-shattering force. The interlocking teeth slice cleanly through prey, often shearing smaller fish entirely in half on the first pass. The Barracuda then immediately violently snaps its head from side to side, ripping the remaining flesh into manageable chunks before swallowing them down. In a matter of seconds, the silver flash of the prey is gone, replaced by a slowly sinking cloud of scales. The Barracuda circles once, its jaw working methodically, and then returns to its silent, suspended vigil at the edge of the blue. In its immediate, visceral theater of survival, the Barracuda is a creature of pure mechanical perfection. It relies entirely on muscle hydrodynamics and precise timing. It does not possess a venom gland. It does not manufacture neurotoxins to paralyze its prey. It does not bristle with toxic spines to deter larger sharks. It is, by all biological definitions, a non-venomous animal. And yet, within the incredibly complex and invisible architecture of the toxic food web, the Barracuda stands as one of the most chemically dangerous organisms a human being can encounter. To understand this terrifying paradox, we must completely shift our perspective. We must pull away from a massive, silver apex predator holding its station in the current and zoom down, far past the schooling fish, past the branching corals, all the way down to the microscopic surface of the dead, algae-covered rubble at the very foundation of the reef. Here, in a world invisible to the naked eye, clings a single-celled microorganism known as a dinoflagellate. Under normal, balanced ecological conditions, these microbes exist in manageable numbers, quietly photosynthesizing and living attached to the blades of turf algae and seaweed. However, the coral reef is a highly sensitive environment. When a reef experiences severe stress, whether from the violent physical destruction of a hurricane, the devastating thermal shock of a coral bleaching event, or the sudden influx of nutrient-rich agricultural runoff from a mainland, the delicate balance shatters. The hard corals die back, and opportunistic algae rapidly colonize the newly exposed limestone. As the algae bloom, the dinoflagellates that live upon them experience a massive, unprecedented population explosion. And it is here that the chemical nightmare begins. These specific microscopic organisms are biological factories, synthesizing a highly complex, lipid-soluble chemical compound. To the microbe, this compound is simply a byproduct of its existence, perhaps a microscopic defense mechanism. But to the complex nervous systems of higher vertebrates, this chemical is known as ciguatoxin. At the microscopic level, the amount of toxin produced by a single cell is infinitesimally small. It is a chemical whisper, but the reef is an engine designed to move energy upward. A small, herbivorous surgeonfish flutters down to the rubble to feed. Using its specialized teeth, it scrapes the algae from a rock. In doing so, it inadvertently consumes thousands, perhaps millions, of the toxic dinoflagellates. The small fish processes the algae for energy, but its digestive system cannot break down the ciguatoxin. Because the molecule is fat-soluble, it slips to the digestive tract and binds securely to the fat reserves, the liver, and the muscle tissues of the surgeonfish. The fish does not die. It does not even appear sick. It simply becomes a swimming, living storage container for the toxin. Days later, a mid-level predator, perhaps a snapper or a medium-sized jack, ambushes the surgeonfish. The jack digests the meat, burning the calories for energy. But once again, the ciguatoxin refuses to be destroyed. It transfers from the flesh of the prey into the flesh of the predator. Because the jack eats hundreds of herbivorous fish over its lifetime, the concentration of the toxin within its own body begins to steadily, inexorably rise. This terrifying process is known as biomagnification. With every single step up the trophic ladder of the food web, the chemical whisper grows louder, concentrating exponentially as it is passed from prey to predator. This brings us back to the edge of the blue, to the silent, hovering form of the great barracuda. As an apex predator, the barracuda sits at the absolute pinnacle of this trophic pyramid. A large, mature individual may have been patrolling the reef for 10 or 15 years. Over that decade, it has consumed thousands of jacks, snappers, groupers, and grunts. It has ingested the accumulated chemical burden of an entire ecosystem. With every successful violent strike, the barracuda adds another microscopic dose of ciguatoxin to its own muscular flanks. It is the ultimate biological vault, collecting and hoarding the toxic history of the reef. The profound irony of this accumulation is that the barracuda remains utterly unaffected by the neurotoxin saturating its tissues. Its physiology has evolved to perfectly tolerate the chemical load. The toxin does not dull its reflexes. It does not blur its vision. It does not slow its explosive acceleration. The barracuda continues to hunt with the same flawless, terrifying efficiency it possessed on its first day of life. To look at the fish is to see a paragon of marine health. Its silver scales catch the light perfectly. Its eyes are clear and focused. Its muscle tone is pristine. There is absolutely no external warning, no foul odor, no discoloration of the flesh to indicate that the animal has been compromised. But it has been. The barracuda has been transformed from a mechanical predator into an incidental chemical weapon. The true danger of the barracuda emerges when it intersects with the human world. A large barracuda is a prize catch for a sport fisherman or a commercial angler. It puts up a spectacular, violently acrobatic fight on the line. When a massive fish is finally hauled onto the deck, it is celebrated as a bounty. The meat is filleted, yielding thick, beautiful white steaks. Here, the resilience of the ciguatoxin reveals its most terrifying characteristic. The toxin is incredibly heat-stable. It is completely impervious to the extremes of human culinary preparation. Freezing the meat solid does not break the molecule. Searing it over an open flame, Boiling it, baking it, or soaking it in highly acidic citrus juices does absolutely nothing to alter the chemical structure of the poison. The human consumes a meal, believing they're eating a pristine, healthy product of the ocean. Within hours, the invisible biological trap snaps shut. Saguaro poisoning is one of the most complex and deeply disorienting marine toxidromes known to medicine. As a digested ciguatoxin enters the human bloodstream, it specifically targets the nervous system. It binds aggressively to the voltage-gated sodium channels located on the membranes of nerve and muscle cells. Under normal conditions, these channels open and close in a highly regulated sequence, allowing electrical impulses to travel along the nerves, controlling everything from the beating of the heart to the sensation of touch. The ciguatoxin acts like a molecular wedge, forcing these critical sodium channels to lock in the open position. The nerves are thrown into a state of continuous, chaotic depolarization. They begin firing wildly, uncontrollably, flooding the brain with a torrential downpour of false signals and agonizing sensory errors. The initial onset is physical and brutal. The victim experiences profound gastrointestinal collapse, severe nausea, vomiting, and abdominal cramping as the body attempts to purge the tainted meal. The cardiovascular system struggles, leading to a dangerous plummet in blood pressure and a slow, irregular heartbeat. But it is the neurological symptoms that define the true horror of saguaro. As the nervous system misfires, the victim's perception of reality is fundamentally altered. They experience intense paresthesia, a severe, painful tingling and numbness that begins in the lips and tongue and rapidly spreads to the hands and feet, feeling as though the extremities are being continuously pierced by thousands of invisible needles. A deep, aching weakness invades the major muscle groups, making the simple act of walking feel like moving through wet concrete. Most bizarre and terrifying of all is the hallmark symptom of saguaro: paradoxical temperature reversal. The misfiring nerves completely scramble the brain's ability to interpret thermal data. A victim attempting to wash their hands in cold water will recoil in agony, their brain registering the sensation as boiling, scalding heat. Conversely, stepping into a hot shower feels like being pelted by shards of freezing ice. The basic, fundamental interaction with the physical world becomes a landscape of pain and confusion. Because ciguatoxin is highly lipophilic, meaning it binds stubbornly to human fat tissues, the body struggles immensely to flush it out. There is no known antidote. The severe neurological symptoms, the profound fatigue, and the agonizing joint pain can persist for weeks, months, or in severe cases, years. A person can be triggered into a sudden relapse of symptoms months after the initial poisoning simply by consuming alcohol, eating certain proteins, or experiencing rapid weight loss, which releases a stored toxin back into the bloodstream. Through this agonizing process, the barracuda achieves a delayed, almost spectral vengeance from beyond the grave. The human hunted the apex predator, seeking to consume its strength and its mass. But in doing so, the human inadvertently consumed the accumulated stress of the entire reef. In this light, the barracuda ceases to be merely a fish. Within the context of the toxic food web, it serves as a massive, swimming ecological ledger. It is a living barometer for the hidden health of the ocean. A reef that produces highly toxic barracudas is a reef that is suffering. It is a reef where the corals have died, where the delicate balance of grazing and growth has been shattered, and where toxic, opportunistic microbes have seized control of the foundational substrate. The barracuda did not create this toxicity, nor does it use it. It simply documents it, storing the chemical history of a changing, struggling environment within its own invincible flesh. As the sun begins to set, the light penetrating the water column shifts from vibrant gold to a deep, bruised purple. The diurnal fish of the reef rush to find shelter in the limestone cracks, terrified of the impending dark. At the edge of the drop-off, the barracuda remains utterly unmoved. It holds its position, a sleek, silver silhouette suspended in the cooling current. Its jaw rests slightly open, its terrifying teeth gleaming faintly in the dying light. It watches the changing of the guard, waiting for the nocturnal prey to emerge. It is a creature of absolute purity, pure speed, pure instinct, pure mechanical perfection. It will strike again tonight and tomorrow and the day after that. It will continue to violently consume the life of the reef, completely unaware of the invisible molecular burden it pulls upward through the water with every meal. It does not sting, and it does not inject. It simply exists as the ocean designed it to, a flawless hunter carrying a hidden, devastating cargo, a silent vessel of consequence, floating patiently at the edge of the abyss. The mid-morning sun penetrates the ocean's surface, casting a brilliant, shifting net of light across the coral shelf. Down here, the reef is not an open arena. It is a sprawling, chaotic metropolis of calcium carbonate. It is a three-dimensional labyrinth of branching antlers, deep fissures, overhanging ledges, and claustrophobic tunnels. In this jagged geometry, the rules of pursuit are fundamentally altered. An apex predator built for explosive speed, like a shark or a tuna, is useless within this dense matrix. If a large predator accelerates too quickly, it shatters against the limestone. A wide jaw cannot fully open inside a narrow crevice. In this tangled architecture, brute force is a liability. The reef heavily penalizes the clumsy and the oversized. Survival in the coral maze belongs exclusively to the agile, the compact, and the incredibly efficient. Slipping through a gap barely wider than a human hand, a serpentine silhouette glides into the dappled light. It moves with a hypnotic, fluid grace that seems to defy the resistance of the water. This is a sea snake. It does not swim with the frantic, fin-slapping panic of a fleeing fish, nor does it possess the rigid, muscular thrust of an eel. Its locomotion is a masterpiece of aquatic adaptation. The entire rear half of its body is laterally compressed, flattened from side to side, culminating in a broad, paddle-like tail. By sending smooth, continuous undulations traveling down its spine, it slices through the dense medium of water with virtually zero turbulence. It leaves almost no wake. It is a creature born of the earth, a descendant of terrestrial reptiles, that has returned to the sea and perfected the art of the silent glide. This silence and efficiency are not just for stealth. They are biological imperatives born of a supreme vulnerability. The sea snake is an air-breathing reptile. It possesses no gills. To survive in the sunken world of reef, it relies on a single, massively elongated lung that stretches almost the entire length of its tubular body cavity. When it surfaces to breathe, it inhales a massive volume of air, which it must meticulously conserve. Every twitch of muscle, every sudden acceleration, burns precious oxygen. Therefore, its entire existence is an exercise in extreme metabolic economy. It cannot afford to engage in exhausting, prolonged physical struggles with its prey. It must hunt, kill, and consume with the absolute minimum expenditure of energy, all while a ticking biological clock urges it back toward the surface. The prey it seeks, the small reef fish, the darting gobies, and the slender moray eels, are perfectly adapted to this environment. They are muscular, slippery, and incredibly fast, designed to vanish into microscopic cracks the instant they sense a shift in water pressure. If a sea snake were to hunt like its terrestrial cousins, the pythons or the rat snakes, it would fail completely. It cannot coil its body around a struggling fish to constrict it. The jagged, branching core would block the coils, and the writhing prey would easily slip away into the labyrinth. Furthermore, the sea snake has a remarkably small, streamlined head with a very modest gape. It cannot unhinge its jaws to swallow massive, struggling prey whole. Evolution faced a daunting engineering problem. How does an air-breathing, small-mouthed predator effectively hunt highly agile prey inside a rigid, unforgiving stone maze without exhausting its limited oxygen supply? The answer was not to build a stronger snake. The answer was to bypass the physical struggle entirely. The evolutionary solution was a breathtakingly potent chemical shortcut. As the snake patrols the reef, it moves like a ribbon of living sensory equipment. Its vision is adequate, but in the shadowed, visually confusing environment of the coral heads, it relies on older, deeper senses. Its forked tongue constantly flickers out into water, tasting the dissolved chemical trails left behind by the mucus and metabolic waste of hidden fish. Simultaneously, specialized mechanoreceptors along its scales read the subtle hydrodynamic pressure waves bouncing off the coral. It can literally feel the localized disturbance of frightened fish breathing inside a dark hole. Guided by this invisible sensory map, the snake threads its way deep into the branching coral. It finds a cluster of small damselfish hovering nervously near a crevice. The snake does not coil to strike. It does not adopt an aggressive, S-shaped posture. The approach is casual, almost deceptively lazy. It simply continues its smooth glide, closing the distance with silent inevitability. When the strike occurs, it is an anticlimax. There is no dramatic, open-jawed lunge. There is only a swift, economical forward snap of the small head. The jaws close around the flank of a fish. The grip is incredibly light. Inside the snake's mouth, situated at the front of the upper jaw, are two short, fixed fangs. They do not fold back like the fangs of a viper. They are permanently erect, grooved needles. The moment the jaws make contact, these fangs puncture the scales and slide into the muscle of the fish. Contractions in the snake's venom glands, located just behind its eyes, force a microscopic droplet of venom down to the fangs and deep into the prey's tissue. The entire physical interaction lasts less than a second. The snake immediately releases its grip. The fish, startled and bleeding slightly, darts frantically away, wedging itself deep into the darkest, most inaccessible reaches of the coral matrix. To an outside observer, it appears the snake has failed. It let the prey go. It lost a meal to the impenetrable fortress of the reef. But the snake does not chase the fleeing fish. It simply waits, holding its position in the water column, calmly tasting the chemical trail of the wounded animal. It knows that the hunt is already over. The physical pursuit has been entirely replaced by a biochemical one, and the venom is doing the chasing. The payload delivered by the sea snake is one of the most concentrated and devastating toxic cocktails in the animal kingdom. It is far more potent than the venom of a cobra or a rattlesnake. It is a highly specialized dual-action weapon composed of deadly neurotoxins and myotoxins. The moment the venom enters the fish's bloodstream, it races toward the nervous system. The neurotoxins are molecular saboteurs. They bind aggressively to the acetylcholine receptors at the neuromuscular junctions, the critical bridges where nerve impulses command the muscles to fire. By blocking these receptors, the venom instantly severs the communication between the fish's brain and its body. At the same time, the myotoxins begin to actively dissolve the muscle fibers themselves, breaking down the proteins necessary for movement. Deep inside its coral sanctuary, the fleeing fish experiences a terrifying, rapid systems failure. The frantic beating of its tail begins to slow. Its fins lose their rigid coordination. A profound, creeping heaviness overtakes it. It tries to thrash, to push itself further into crack, but the muscles refuse to answer frantic firing of its brain. Within seconds, a total, flaccid paralysis sets in. The fish simply stops moving, locked in place, breathing its last, shallow breaths. Outside the crevice, the sea snake smoothly follows the fading chemical trail. It glides perfectly into the narrow hole, its streamlined head encountering no resistance. It finds a paralyzed fish waiting in the dark, entirely incapable of fighting back. With deliberate ease, the snake opens its small jaws, grasps the fish by the head, and slowly begins to swallow it whole. This is the genius of the sea snake's design. By utilizing a venom that guarantees rapid, total incapacitation, the snake turns the reef's defenses against the prey. The fish does all the hard work of wedging itself into a secure, enclosed space where larger scavengers cannot steal the meal. The snake simply waits for the chemical shutdown, enters the hole, and dines in complete safety. There is no wrestling match to drain the snake's oxygen. There is no violent thrashing that could damage the snake's delicate eyes against the sharp coral. The venom is the ultimate equalizer, transforming a chaotic, high-energy chase into a calm, guaranteed extraction. This extreme efficiency extends to the snake's venom management. It is a common misconception that venomous animals are biological berserkers, emptying their glands at the slightest provocation. Venom is an incredibly complex cocktail of proteins and peptides. Synthesizing these molecules requires a massive investment of metabolic energy, calories that the snake must replace by hunting. Therefore, venom is a precious resource, an internal bank account that must be carefully managed. Studies of sea snake behavior reveal that they are masters of venom metering. They possess the neurological control to decide exactly how much venom to inject with every single bite. When striking a small, fragile goby, the snake delivers only a microscopic fraction of a drop, just enough to induce paralysis without wasting resources. The snake calculates the mass of the target and the geometry of the escape route, adjusting its chemical investment accordingly. It is a predator operating with the cold, calculated logic of an accountant. This clinical efficiency is directly responsible for the sea snake's surprisingly docile reputation among human divers. Given the overwhelming potency of their venom, one might expect sea snakes to be the terrors of the deep, aggressively attacking anything that approaches. The reality is profoundly different. In the open water, sea snakes are overwhelmingly indifferent to the presence of humans. They will frequently swim directly past divers, sometimes even investigating a camera lens or the flutter of a fin with flicking tongues, before smoothly continuing on their way. They do not perceive humans as prey. We are vastly too large for their small jaws to consume, and because they view venom as a precious, metabolically expensive hunting tool, they are loath to waste it on a defensive strike against an animal they cannot eat. Biting a human represents a catastrophic loss of biological capital. Consequently, bites to humans are exceptionally rare. They almost exclusively occur when the animal is actively manhandled, stepped on in shallow water, or violently pulled from the ocean in the chaotic, terrifying environment of a commercial fishing net. When pushed to the absolute brink, forced to defend its life, the snake will strike. If that tragic intersection occurs, the terrifying elegance of the sea snake's venom is unleashed upon the human nervous system. Because the fangs are so small and the venom is designed for stealthy efficiency rather than creating a painful deterrent warning, the initial bite is often described as entirely painless. A fisherman might feel nothing more than a faint prick akin to a mosquito bite and dismiss it completely. There is no immediate, searing agony like the sting of a stonefish. There is no massive, localized swelling. This absence of pain creates a deadly, deceptive window of calm. For the first hour or two, the victim may feel completely normal. But beneath the surface, the neurotoxins are silently locking down the neuromuscular junctions. The first subtle symptoms are a feeling of heaviness in the tongue, a slight blurring of vision, and a stiffening of the jaw. This is followed by a creeping, systemic weakness in the major muscle groups of the legs and arms. As the hours pass, the paralysis marches relentlessly inward toward the core of the body. The victim remains entirely lucid, their cognitive functions perfectly intact, as they slowly lose the ability to move, to speak, and to swallow. The ultimate, fatal conclusion of the envenomation is not a dramatic cardiovascular collapse. It is respiratory failure. The diaphragm, the massive muscle responsible for pulling air into the lungs, simply receives a chemical command to stop working. Without advanced medical intervention and mechanical ventilation, the victim suffocates, their body completely silenced by a few milligrams of protein designed to immobilize a tiny fish in a coral crack. The venom is not cruel. It is simply optimized. It is a chemical key perfectly cut to shut down a vertebrate nervous system, utterly indifferent to whether that system belongs to a moray eel or a human being. The sea snake's mastery of the ocean is absolute. While marine iguanas must drag themselves onto scorching rocks to warm their bodies, and sea turtles must haul their massive bulk onto sandy beaches to bury their eggs, many species of sea snake have entirely severed their physical connection to the land. They are the truest of marine reptiles. They mate in the water column, a twisting, serpentine dance suspended in the blue. And, perhaps most remarkably, they have evolved the ability to give birth to live young. The female retains the developing embryos within her body, acting as a living, swimming incubator. When the time comes, she seeks out the quiet shelter of a deep coral cave and delivers fully formed, perfectly capable miniature snakes directly into the ocean. From the moment they take their first gulp of air at the surface, they are fully armed, independent hunters, perfectly adapted to the three-dimensional geometry of the reef. They will live, hunt, reproduce, and eventually die, all without ever once touching solid ground. To watch a sea snake patrol the reef is to observe the perfect intersection of physical limitation and biochemical brilliance. The jagged, unforgiving architecture of the coral dictated the rules of the game. Speed is dangerous, space is tight, and air is limited. The sea snake accepted these constraints. It discarded the heavy musculature of the constrictor. It abandoned the massive, drag-inducing jaws of the viper. It streamlined its form into a perfect hydrodynamic paddle, and it outsourced the violent, exhausting work of the kill to a microscopic droplet of quiet, devastating chemistry. It moved through the chaotic metropolis of the reef not with the explosive violence of a shark, but with the serene, untouchable confidence of an assassin who knows that the battle is won the moment contact is made. It is a creature shaped by constraint, surviving in a fast, violent world by mastering the dark, elegant art of the silent shutdown, where the towering, chaotic architecture of the coral reef finally yields to the open expanse of the lagoon. A profound transition occurs. The vertical cliffs of limestone give way to a flat, seemingly endless desert of pale, rippled sand. This boundary zone is a place of stark contrast. The reef is a dense, high-stakes metropolis of hiding places, sudden ambushes, and heavily armored combatants. The sand, by comparison, is an exposed wasteland. There is nowhere to hide, no crevice to slip into, and no shadowed overhang to seek refuge beneath. For most of the reef's inhabitants, venturing out onto this flat, illuminated plain is an invitation to immediate predation. Yet, inching its way across this perilous, open ground, completely exposed to the filtered sunlight and the gaze of every passing predator, is an animal that appears to have given up entirely on the concept of self-defense. It looks less like a living creature and more like a discarded length of mottled, waterlogged rope. Its body is tubular, soft, and profoundly sluggish, painted in dull, muddy hues of olive, brown, and gray that simply mirror the sediment beneath it. It possesses no heavily calcified shell into which it can retreat. It has no razor-sharp spines to ward off a bite. It carries no vibrant, neon warning colors to advertise danger, nor does it possess even a fraction of the muscular power required to flee. In an ecosystem defined by teeth, venom, and explosive speed, the sea cucumber appears to be a walking biological mistake. It seems to be nothing more than a slow-moving, unprotected meal waiting to be claimed. But the coral reef does not tolerate the defenseless. To survive in the open, the sea cucumber has evolved a strategy that completely rewrites the rules of engagement. It does not fight. It does not run. Instead, it relies on a form of biochemical warfare so intensely unpleasant that it turns the animal into a masterpiece of weaponized inconvenience. To understand the sea cucumber, one must look past its unassuming, sausage-like exterior and examine the bizarre evolutionary lineage from which it descends. It is an echinoderm, placing in the same family tree as the star-shaped sea stars and the fiercely spiked sea urchins. However, over millions of years, the sea cucumber took the rigid, spherical body plan of its ancestors and stretched it out, laying it flat upon the seabed. It abandoned the heavy, interlocking plates of calcium carbonate that armor a sea urchin. In their place, the sea cucumber developed a thick, leathery skin supported by a hidden, microscopic framework. Embedded deep within its connective tissue are millions of tiny, bone-like structures called calcareous ossicles. These microscopic plates provide the animal with enough structural integrity to hold its shape, while allowing its body to remain incredibly flexible, capable of squeezing through narrow gaps or contouring to the uneven floor of the ocean. Along its underside runs a network of hundreds of tiny, hydraulic tube feet, powered by an internal water vascular system. These feet constantly extend, grip the grains of sand, and contract, pulling the animal forward in a creeping, agonizingly slow procession. At the leading edge of this crawling cylinder is a mouth, surrounded by a crown of specialized, branching tentacles. These tentacles are primary tools of its trade, for the sea cucumber is a great, tireless recycler of the ocean floor. As it creeps across the barren plains, the tentacles constantly sweep the substrate. They act like sticky, biological mops, gathering up the fallen organic detritus, the dead algae, the microscopic plankton, the settled waste, and the decaying matter that constantly rains down from the bustling reef above. The sea cucumber shovels the sediment into its mouth, passing it through a long, winding digestive tract. Its internal organs strip the sand of every available calorie and nutrient, before expelling the clean, processed sand out the other end. This unglamorous existence, the endless, slow-motion consumption of the ocean's waste, is of paramount ecological importance. The sea cucumber is the earthworm of the sea. By constantly ingesting and excreting the sand, a process known as bioturbation, it prevents the seabed from becoming compacted and suffocated. It turns the sediment over, aerating the floor, preventing the buildup of toxic, oxygen-deprived zones, and redistributing vital nutrients back into the water column to feed the base of the food web. Without the silent, endless labor of the sea cucumbers, the majestic coral reef bordering the sand would slowly choke on its own accumulated decay. Yet this vital, slow-moving labor leaves the animal entirely exposed. A foraging triggerfish or a prowling snapper, scanning the bottom for an easy meal, will easily spot the sluggish cylinder. The predator swims down, anticipating an effortless kill. There is no chase. There is no dramatic evasion. The fish moves in to take a massive, crushing bite. But long before the jaws can close around the soft flesh, an invisible threshold is crossed. The sea cucumber does not need to be bitten to initiate its defense. The mere physical disturbance of the approaching predator, the sudden shift in water pressure or a tentative, investigative nudge is enough to trigger a devastating chemical response. The sea cucumber possesses specialized secretory cells embedded throughout its leathery body wall. When stressed, these cells instantly dump a payload of highly complex chemical compounds directly into the surrounding water. These compounds are called saponins. They are not venoms injected through a hollow fawn, nor are they toxins that must be swallowed to take effect. Saponins are powerful, surface-active molecules that behave remarkably like biological detergents. They have the ability to bind with cholesterol, fundamentally disrupting the structural integrity of cellular membranes. When the sea cucumber releases its saponins, it essentially detonates an underwater chemical smoke grenade. The water in the immediate vicinity of the animal instantly becomes a localized zone of intense toxicity. For the approaching fish, the effect is immediate and deeply distressing. A fish's most vulnerable anatomical feature is its gills, the delicate, highly permeable, blood-rich tissues it relies upon to extract oxygen from the water. As the predator swims into the invisible cloud of saponins, these detergent-like molecules wash directly over the gills. The saponins violently attack the cellular membranes of the respiratory tissues. It is the aquatic equivalent of inhaling a cloud of tear gas and pulverized glass. The predator experiences severe, instantaneous irritation and a terrifying disruption of its ability to breathe. It begins to choke in the very water it relies on for life. The reaction is universally violent. The fish violently shakes its head, coughing and flushing water back out through its gill covers in a desperate attempt to clear the burning sensation. It immediately abandons the attack, darting away from the slow-moving cylinder, its desire for a meal completely erased by the overwhelming, suffocating discomfort. The brilliance of the sea cucumber saponin defense lies in its ability to dictate the boundaries of the encounter. It does not need to overpower the predator. It simply changes the chemical composition of the battlefield, making the very act of proximity intolerable. The defense radiates outward, punishing not only the direct attacker, but anything swimming too close. Over countless generations, this invisible shield has profoundly shaped the psychology of the reef's predators. The ocean is a landscape of learned behaviors, and inhabitants of the reef have learned through painful, choking experience that the slow, fleshy tubes on the sand are a terrible biological investment. Fish that actively graze the substrate will swim right past the sea cucumber, ignoring it completely as they hunt for crabs, worms, or mollusks. The sea cucumber survives by cultivating a reputation of absolute unpalatability. It is simply not worth the misery. But nature is rarely absolute, and occasionally, a predator is desperate enough or inexperienced enough to push through the chemical cloud. Sometimes, a crab will manage to secure a painful, pinching grip, or a highly motivated fish will attempt to endure the burning gills long enough to tear a chunk of flesh from the sea cucumber's body. When the primary deterrent fails and the threat of catastrophic physical damage becomes real, the sea cucumber escalates its defense to a level of bizarre, sacrificial extremity. Sensing the violent physical trauma, the animal fiercely contracts the powerful muscles running the length of its body. The internal hydrostatic pressure spikes dramatically. Then, in an act of biological desperation, the sea cucumber turns its hindquarters toward the attacker and violently expels a portion of its own internal organs out through its cloaca. These specialized organs are known as Cuvierian tubules. Inside the cucumber, there are a cluster of blind-ending, spaghetti-like tubes attached to the base of the respiratory tree. But the moment they are violently ejected into the seawater, their physical properties undergo a radical, terrifying transformation. Upon contact with the ocean, the tubules rapidly absorb water, elongating to incredibly up to 20 times their original length in a fraction of a second. They erupt outward into the water column like a barrage of white, chaotic, silly string. But this is not a harmless distraction. The surface of these elongated threads is coated in an extraordinarily powerful, specialized adhesive. As the predator thrashes against the sea cucumber, it inevitably collides with the expanding mass of tubules. The moment the threads touch the predator, they stick with the tenacity of industrial superglue. The more the fish struggles to tear itself free, the more it wraps itself in the expanding, sticky web. The threads bind the predator's fins, locking them to its sides. They smear across its eyes, blinding it. They clog its mouth and wrap tightly around its gills. Furthermore, these tubules are heavily laced with the same highly concentrated, toxic saponins that the cucumber secretes from its skin. The predator is not only physically mobilized, bound and gagged by a chaotic net of living tissue, but it is simultaneously subjected to a massive, localized dose of the membrane-destroying chemical. The attack is completely neutralized. The fish, now fighting a desperate battle merely to free itself and survive, thrashes wildly on the sand, completely forgetting the prey it had intended to consume. Meanwhile, the sea cucumber, seemingly maimed and bleeding, slowly crawls away from the chaotic scene. It has sacrificed a significant portion of its internal anatomy, a tactic that seems biologically ruinous. However, this dramatic sacrifice is underpinned by one of the sea cucumber's most extraordinary biological superpowers, the capacity for extreme cellular regeneration. The loss of the cuvarian tubules, and even portions of its digestive tract expelled during extreme stress, is not a fatal blow. The sea cucumber is a master of rebuilding itself. Once it reaches safety, it initiates a complex process of cellular division and tissue remodeling. Over the course of a few weeks or months, it will perfectly regenerate the lost organs from scratch, entirely replenishing its bizarre, sticky arsenal. This regenerative capability frames the entire evolutionary economics of the sea cucumber's existence. In the harsh accounting of the wild, everything has a cost. Developing a heavy, impenetrable shell requires a massive, constant intake of calcium and calories. Maintaining the powerful, fast-twitch musculature required for high-speed evasion demands a roaring, high-energy metabolism. The sea cucumber rejected both of these costly strategies. It opted for an existence of minimal metabolic overhead. It crawls slowly. It eats the garbage of the ocean. It demands very little from its environment. And instead of investing in heavy armor or speed, it invested its evolutionary capital entirely into chemical deterrence and unparalleled resilience. It can afford to be soft, and it can afford to be slow, because it has perfected the art of making itself biologically repulsive. It is willing to sacrifice pieces of its own body, because it holds the genetic blueprints to simply grow them back. Yet, this brilliantly optimized system of survival is deeply tethered to the physical conditions of the ocean. The sea cucumber is an ectotherm, meaning its internal temperature, and consequently its metabolic rate and physiological health, is entirely dictated by the surrounding seawater. As global climate change drives the temperature of the ocean steadily upward, the sea cucumber finds itself facing an invisible threat that its saponins cannot repel. Unnaturally warm waters induce profound physiological stress in these slow-moving animals. As their internal temperature rises, their metabolism races, placing massive energetic demands on a system designed for slow, low-energy efficiency. Furthermore, extreme thermal stress can severely disrupt the complex biochemical pathways required to synthesize the defensive saponins. A heat-stressed sea cucumber is a weakened sea cucumber, potentially incapable of producing the dense chemical cloud required to ward off predators. This vulnerability is compounded by the animal's reproductive strategy. To ensure the continuation of their species, sea cucumbers rely on broadcast spawning. During specific, synchronized phases of the moon, driven by temperature and tidal cues, male and female sea cucumbers scattered across the lagoon will simultaneously rise up. They use their tube feet to anchor their lower halves to the sand, while lifting the anterior portion of their bodies high into the water column. In this bizarre upright posture, looking like small fleshy towers swaying in the current, they release massive clouds of sperm and eggs directly into the sea, trusting the tide to mix and fertilize the next generation. It is a moment of absolute, terrifying exposure. The animal lifts itself out of the camouflaging sand, waving its body in the open water. Yet, even in this highly vulnerable, upright stance, the chemical shield holds. The saponins within the skin continue to radiate their invisible deterrence, protecting the spawning adults during the most critical moment of their life cycle. The true tragedy of the sea cucumber is that its flawless, millions of years old defense system is entirely useless against the one predator operating outside the evolutionary rules of the reef: humans. In many parts of the world, particularly in Asian markets, the dry body wall of the sea cucumber, known as bêche de mer or trepang, is a highly prized culinary delicacy and a component of traditional medicine. A human diver descending to the seabed is completely immune to the saponin cloud. They wear masks to protect their eyes, and they do not breathe the water. The human simply reaches down, picks up the slow-moving animal, and places it in a bag. Because the sea cucumber's entire survival strategy relies on deterring predators, not escaping them, it is exceptionally vulnerable to targeted overharvesting. It cannot swim away. It cannot hide. Entire lagoons can be systematically stripped of their sea cucumber populations in a matter of weeks. When the sea cucumbers are removed, the ecological consequences for the reef are profound and devastating. Without the silent, tireless army of detritivores churning and cleaning the sand, the sediment begins to compact. The organic waste from the reef above accumulates, rotting in the stagnant sand. Oxygen levels plunge, creating toxic and noxic dead zones on the lagoon floor. The nutrient cycling that feeds the base of the food web grinds to a halt, and the surrounding coral reefs, starved of recycled nutrients and choked by unchecked sediment, begin to suffer and decline. The sea cucumber, in all its sluggish, unassuming glory, is a structural pillar of the marine ecosystem. It is a creature that proves that power in the natural world is not always defined by a crushing bite, a venomous sting, or blinding speed. Sometimes, absolute survival belongs to the creature that embraces slowness. It belongs to the animal that turns its own flesh into a chemical boundary and its own organs into a sticky, sacrificial snare. As the sun sets over the lagoon, painting the water in deep indigos and fading golds, the sea cucumber continues its relentless, creeping march. It sweeps its tentacles across the sand, processing the decay, turning the endless wheel of life and death on the ocean floor. A passing stingray glides silently overhead. A hunting grouper drifts by in the shadows. They look at the soft, fleshy cylinder exposed on the sand, and they turn away. The sea cucumber does not need to fight the reef. It simply crawls forward in the dark, protected by the invisible, choking power of its own chemistry, a master of survival through the sheer force of biological inconvenience. At the precipice of a coral slope, with a vibrant, sunlit architecture, the shallows begins its steep descent into the deeper, darker blue. The fundamental rules of the reef are constantly enforced. It is an arena of perpetual anxiety. Here, the vast majority of predators move with a calculated, nervous tension. They hug the jagged contours of the rock. They utilize the shifting shadows as cloaks, and they calculate their strikes with desperate, energy-burning speed. Vulnerability is the ultimate sin in this ecosystem, and visibility is often a death sentence. Yet, drifting outward from the shelter of coral overhang, completely ignoring these ancient laws of caution, comes a creature of breathtaking, almost insolent composure. It does not dart. It does not scurry. It advances into the open, unprotected water column with the slow, deliberate pacing of a reigning monarch. Its body is wrapped in a stark, unmissable mosaic of maroon, white, and deep brown vertical stripes, a pattern that completely severs it from the muted background of the reef. Fanning out from its sides are massive, incredibly ornate pectoral fins, trailing through the water like the silken sleeves of an elaborate gown. Above its back, a crown of rigid, elongated spines rises in a majestic, terrifying halo. This is a lionfish. In a landscape where survival typically depends on either aggressive speed or flawless invisibility, the lionfish behaves like an animal that expects the entire ocean to step aside and accommodate its passage. To understand its profound arrogance, one must look closely at the biological crown it wears. Along the dorsal ridge, the lionfish possesses a row of needle-sharp, rigid spines. Unlike the stonefish, which buries its weapons beneath flesh and algae, or the stingray, which keeps its daggers sheathed and hidden in the sand. The lionfish broadcasts its armory to the world. It is the absolute antithesis of camouflage. Each of these prominently displayed dorsal rays is deeply grooved, and seated at the base of these grooves are highly specialized venom glands. The lionfish does not use these spines to hunt. It cannot launch them, and it does not aggressively ram them into its prey. The spines constitute a purely defensive perimeter, but they are a perimeter built on the promise of agonizing chemical retaliation. When a larger predator, a cruising shark or a hungry grouper, spots this slow-moving, brightly colored morsel, the visual spectacle invites a devastating lesson. If the predator ignores the vivid warning colors and attempts to snap its jaws around the lionfish, the rigid spines are driven into the attacker's mouth. The mechanical pressure of the bite squeezes the venom glands, forcing a highly toxic, protein-based payload up through the grooves and directly into the predator's tissues. The resulting envenomation is immediate and excruciating. The venom is designed to trigger massive localized pain, accompanied by severe swelling and systemic physiological distress. It is a chemical shock to the system that instantly overwrites the predator's desire to feed. The attacker violently regurgitates the lionfish and flees, its mouth burning with a painful memory that will likely alter its foraging behavior for the rest of its life. Through this agonizing trial and error, the predator community of the native Indo-Pacific Reef has learned a crucial, universal truth. The cost of consuming a lionfish is simply too high. It is this absolute, unshakable chemical security that completely rewrites how the lionfish interacts with its world. Because it faces virtually no threat of predation once it reaches maturity, it is emancipated from the exhausting, fear-driven existence of a typical reef fish. It does not need to burn precious calories darting between hiding places. It does not need to expend energy maintaining complex camouflage. The venom acts as a biological shield, and behind that shield, the lionfish has developed a hunting strategy built entirely on patience, geometry, and psychological manipulation. When the lionfish decides to hunt, it does not rely on the explosive, muscle-tearing acceleration of a barracuda. Instead, it patrols the coral heads and rocky crevices at a measured, almost hypnotic pace. It targets the small, agile reef fish and crustaceans that make their homes in the complex limestone matrix. As it slowly approaches a small school of damselfish hovering near a rock face, the lionfish deploys its magnificent anatomy. It spreads its massive, oversized pectoral fins outward to their absolute maximum extension. To the tiny prey, these expansive, striped fins suddenly appear as a vast, impassable wall. The lionfish uses these fins like a living fence. With agonizing slowness, it advances, using the visual obstruction of its fins and the subtle, invisible displacement of water to gently corral the panicked prey. It herds the smaller fish, cutting off their lateral escape routes, slowly pushing them backward until they are pinned against a vertical wall of coral or backed into a blind corner. The trapped fish dart frantically back and forth, looking for a gap in the slowly advancing, striped barricade. But the lionfish remains perfectly calm. It waits until the geometry is absolute, until the prey is confined to an impossibly tight space. Then, the illusion of slowness vanishes. The lionfish executes a lightning-fast forward lunge, simultaneously expanding its incredibly large, cavernous mouth. This rapid expansion creates a sudden, massive vacuum in the water. Before the cornered prey can even twitch its tail to flee, it is violently sucked forward, pulled into the dark void of the lionfish's throat in a fraction of a second. The jaws snap shut. The massive fins fold back slightly. The lionfish swallows, entirely unbothered, and slowly resumes its hovering patrol. This hunting technique, the slow corral followed by the suction strike, is a masterpiece of energetic efficiency. By forcing the prey into a corner where evasion is physically impossible, the lionfish completely eliminates the need for a high-speed, exhausting chase. It conserves its caloric energy, relying on spatial manipulation rather than brute force. Furthermore, the extended fins create a profound optical illusion to the prey, and to any other predators watching from the periphery. The flared fins make the lionfish appear vastly larger than it actually is. This visual amplification, backed by the very real threat of the venomous spines, ensures that a lionfish is rarely interrupted during its hunt. It transforms what is essentially a slow, biologically vulnerable animal into an undisputed master of the daytime reef, operating conspicuously in broad daylight, while other hunters wait for the cover of darkness. However, the very perfection of this biological design, this flawless intersection of venomous deterrence, visual warning, and hyper-efficient hunting, has given rise to one of the most catastrophic ecological crises in the modern ocean. When an organism is perfectly balanced within its native ecosystem, its numbers are kept in check by a complex web of ancient, co-evolved relationships. But when the lionfish was artificially introduced by humans into the waters of the Western Atlantic, the Gulf of Mexico, and the Caribbean, it was dropped into an ocean that had absolutely no evolutionary memory of its existence. In its native Indo-Pacific, predators recognized the lionfish's warning stripes, and parasites and diseases native to that ocean helped keep its population in check. In the Atlantic, the lionfish is an alien invader. When a native Caribbean predator, a snapper, or a juvenile grouper sees a lionfish hovering over the reef, it does not see a toxic threat. It sees a slow-moving, brightly colored target. It approaches with predatory intent, completely ignorant of the danger. The inevitable consequence is a face full of venomous spines. The native predators learn quickly, but the lesson they learn is avoidance. They realize this new, bizarre fish is untouchable. This absence of recognition grants the lionfish absolute immunity in a foreign sea. With no natural predators willing to hunt them, the lionfish population experiences a terrifying, exponential explosion. This population boom is supercharged by the animal's staggering reproductive capacity. The lionfish does not breed merely once a season. In the warm, welcoming waters of its invaded territory, a single mature female lionfish can release buoyant, gelatinous egg masses every few days, entirely year-round. A single female is capable of producing upwards of 2 million eggs in a single year. These egg masses drift freely on the ocean currents, dispersing the next generation of heavily armed invaders across thousands of miles of pristine coastline before they finally settle onto new reefs. The ecological devastation that follows is profound and terrifyingly rapid. Because the lionfish requires so little energy to hunt, and because it has no fear of being hunted itself, it becomes a gluttonous, insatiable vacuum. It consumes a staggering variety of native reef fish and crustaceans. Its stomach can expand to accommodate meals nearly half its own body size. The impact ripples violently through the entire food web. The lionfish heavily targets the small, herbivorous fish, the parrotfish, the tangs, and the wrasses that perform the vital task of grazing on algae. These small herbivores are the lawnmowers of the reef, keeping the aggressive, fast-growing algae from suffocating the slow-growing corals. As the lionfish systematically devours the herbivores, the lawnmowers disappear. Without them, the algae experience a massive, unchecked bloom. It grows rapidly over the limestone substrate, choking the mature corals, blocking the sunlight they need to survive, and preventing new, juvenile corals from settling on the rock. In a matter of a few seasons, a vibrant, diverse coral reef can be completely overrun by algae, its entire foundational structure collapsing simply because a single, venomous predator was introduced at the top of the chain. The slow, confident hunting style made possible by its chemical protection allows the lionfish to forage extensively throughout the entire day, stripping the reef of its life while the native predators rest. Its very presence fundamentally alters the behavior of the surviving prey. Small native fish, terrified of the slow, inevitable approach of the flared fins, abandon their preferred feeding grounds. They retreat deeper into the crevices, clustering in suboptimal habitats where food is scarce but refuge is marginally better. The reef becomes a landscape paralyzed by a slow-moving, untouchable tyrant. Even the lionfish's relationship with its environment is dictated by its cold-blooded biology. As an ectotherm, its metabolic rate fluctuates directly with the ambient water temperature. In the warmer tropical shallows of the Caribbean, its digestion accelerates, driving it to feed with even greater frequency and supporting its relentless reproductive cycle. But even when winter currents bring cooler waters and the lionfish's metabolism slows down, its lethality remains entirely undiminished. It may hunt less often, but its venomous spines are unaffected by the cold. The deterrent is permanent, regardless of the animal's metabolic pace. Observing the interactions around a lionfish reveals the incredible nuance of the reef's chemical politics. Despite being covered in toxic weaponry, the lionfish is not a mindless killing machine. In its native waters, it relies on the services of tiny cleanerasses, small fish that boldly swim up to larger predators to pick off dead skin and harmful parasites. When a cleaner fish approaches a lionfish, a remarkable negotiation takes place. The lionfish recognizes a distinctive swimming pattern and coloration of cleaner. It does not flare its fins. It does not angle its venomous spines toward the tiny fish. Instead, it enters a state of near trance, flaring its gills and allowing the cleaner fish to swim directly into its cavernous mouth and navigate the dangerous forest of dorsal spines. This tolerance proves that the lionfish possesses a cognitive ability to distinguish between a threatening pressure and a benign, symbiotic contact. It is perfectly capable of maintaining delicate, mutually beneficial relationships, even while remaining heavily armed. It chooses when it deploys deterrence. The tragic irony of the lionfish's success in the Atlantic is that its ultimate triumph is rooted entirely in the perfection of its chemical defense. Most predators in the ocean are forced to balance risk and reward carefully. They must weigh the caloric gain of a meal against the caloric cost of the chase and the physical danger of exposure. The lionfish, insulated by its venom, has completely bypassed this calculation. It operates with a visible, undeniable arrogance. It occupies the open water column, hunting in broad daylight, abandoning stealth entirely. This arrogance is not reckless stupidity. It is biological confidence, enabled entirely by a safety net of toxic proteins that shifts the fundamental cost-benefit analysis of survival. The spines reduce the need for secrecy, allowing the evolution of a hunting strategy built purely on patience and spatial manipulation. It is a creature that proves that venom does not merely inflict pain. It buys time. It buys space. It buys the luxury of moving slowly in a world that demands speed. As the ocean currents ripple across the coral heads, the lionfish continues its deliberate, unhurried patrol. The small native fish of the reef scatter, reforming their nervous schools at a distance, their eyes locked on the approaching striped silhouette. They calculate their escape routes, watching in terror as the available space narrows under the sweeping spread of those elegant, cloaking fins. A swift, sudden surge forward. A brief, violent vacuum in the water. Another piece of the reef's life disappears into the dark. The hunter immediately slows, its fins fanning out once more. It resumes its poised, majestic drift. It is completely unhurried, utterly conspicuous, and entirely untouchable. In this corner of the ocean, the venom does not accelerate the strike. It does not kill the prey. Instead, it creates an impenetrable fortress around the predator, granting it the ultimate, devastating confidence to strike at its absolute leisure. As the afternoon light begins to bruise into the deep violets of evening, a profound shift in tension ripples across the coral reef. The vibrant, busy choreography of the daytime inhabitants, the shimmering schools of chromis and the frantic, grazing parrotfish, starts to wind down. Shadows stretch and lengthen, bleeding into the labyrinthine corridors of the limestone. During the heat of the day, much of the reef's architecture appeared smooth, even barren in places. But as the sun dips below the horizon, the stone itself seems to wake up and grow teeth. From the deepest, darkest recesses of the coral heads, rounded, obsidian forms begin to creep outward. They emerge from the very cracks and chimneys where they've been wedged since dawn, hiding from the prying eyes of visually hunting predators. Slowly, almost imperceptibly, they occupy the ledges and the flats. Where there was once bare rock, there is now a bristling, shifting forest of needles. This is a sea urchin. To the casual observer, the sea urchin might appear to be one of the simplest life forms on the reef, little more than a globe covered in spikes. But this simplicity is a masterful biological deception. The sea urchin is an organism of extraordinary structural engineering and mathematical precision. The core of the animal is a rigid, spherical shell known as a test. Far from being a random collection of bone, the test is a sophisticated mosaic of 10 interlocking calcium carbonate plates, fused together in a pattern that echoes the fivefold symmetry found in its cousins, the sea stars. Every millimeter of this armor is functional. This is a fortress that lives. Upon this rigid test is mounted the urchin's primary layer of defense, the spines. These are not static, brittle protrusions. Each spine is an individual masterpiece of mechanical design, articulating on a complex ball and socket joint. This allows the urchin to move every single needle independently, rotating them with incredible fluidity. The urchin does not need to see a threat to respond to it. It is covered in a diffuse network of light-sensitive cells and mechanoreceptors that allow it to read the environment in 360 degrees. When a shadow passes overhead or a sudden shift in water pressure signals the approach of a predator, the urchin does not flee. Instead, it engages in a coordinated defensive pivot. In a wave of silent motion, it angles its entire canopy of spines toward the source of the disturbance. It presents a world with a hemisphere of impenetrable sharp points, creating a physical barrier that makes the animal virtually untouchable. But the sea urchin's arsenal is not limited to these long, primary lances. Hidden between the bases of the spines are thousands of tiny, specialized structures called pedicellariae. These are microscopic, three-jawed pincers mounted on flexible stalks. They function as an active biological cleaning and defense crew. They snap at anything that attempts to settle on the urchin's skin, parasites, drifting algae, or the soft tissues of an inquiring predator. In many tropical species, these tiny pincers are equipped with their own independent venom glands. The defense is incremental and persistent. A predator attempting to take a bite does not encounter a single point of failure. It encounters a collected geometry of pain. The long spines distribute the force of the bite across dozens of sharp tips, making it impossible for a jaw to secure a grip without being pierced multiple times. Many of these spines are designed to be brittle at the tips, breaking off inside the flesh of the attacker and remaining there, causing immediate inflammation and potential infection. If the predator persists, the venomous pedicellariae snap shut on the sensitive tissues of mouth and eyes, delivering localized toxins that amplify the trauma. This relentless mechanical and chemical deterrence has a profound impact on the spatial politics of the reef. The sea urchin is a master of environmental partitioning. When urchin densities are high, the reef floor effectively becomes a minefield. Large, opportunistic predators like groupers and wrasses are forced to alter their hunting routes. They cannot simply graze or lunge over the substrate with impunity. They must navigate the narrow, safe corridors between the spiked globes, and every detour they take is a missed opportunity for a meal. The urchin does not need to chase its competitors away. It simply makes the act of existing in its vicinity prohibitively expensive. However, the reef is an arena of endless innovation, and the urchin's fortress is not unbreachable. The arms race of the coral matrix has produced specialists designed specifically to bypass these needle-clad defenses. Consider the triggerfish. Equipped with exceptionally strong, beak-like jaws and a high degree of tactical intelligence, the triggerfish has learned that the urchin's ultimate vulnerability is its orientation. The triggerfish will approach a sea urchin and use a jet of water from its mouth to try and destabilize it. If that fails, it will boldly grab a single spine and violently flip the urchin over. On its underside, the urchin is relatively unprotected, its spine shorter and its soft mouth parts exposed. Once the urchin is inverted, the triggerfish can use its powerful teeth to crack open the rigid test and consume the nutrient-rich interior. In colder, temperate waters, the sea otter has taken this counter-strategy to an even higher level of sophistication. Otters will dive to the seafloor, gather urchins, and carry them to the surface. Floating on their backs, they place a flat stone on their chest to serve as an anvil and use another stone to smash the urchin's test. This use of tools transforms the urchin from an impenetrable fortress into a manageable, calorie-dense meal. These predator adaptations prove that the urchin's defense is not a guarantee of safety, but a selective pressure. It filters out the weak and the inexperienced, ensuring that only the most highly adapted or intelligent predators can successfully exploit the urchin as a resource. While the urchin's defense is its shield, its mouth is its primary tool of ecological transformation. On its underside, at the very center of the test, lies one of the most complex feeding structures in the animal kingdom, Aristotle's lantern. This is a powerful five-sided arrangement of calcareous teeth and muscles that can be extended, retracted, and manipulated with incredible force. The sea urchin is a voracious, tireless grazer. It moves across the reef at a glacial pace, using its Aristotle's lantern to scrape away at the substrate, grinding down tough macroalgae and encrusting organisms. In a healthy, balanced ecosystem. This grazing is a vital service. The urchins act as the gardeners of the reef, preventing fast-growing algae from overrunning the coral heads and ensuring that juvenile coral polyps have a clean surface on which to settle and grow. They maintain the competitive balance that allows the reef to remain a diverse, multi-layered habitat. But when the delicate balance of food web is shattered, often by the human overharvesting of top-down predators like large fish and lobsters, the sea urchin population can experience a catastrophic, exponential explosion. Without predators to keep their numbers in check, the urchins become an unstoppable grazing force. A massive boom in urchin numbers can transform a vibrant, algae-rich reef into what ecologists call an urchin barren. The collective grazing pressure of thousands of urchins becomes so intense that they strip the substrate of every scrap of vegetation. They don't just eat the algae, they grind away at the very limestone itself. The reef is converted into a sterile, white landscape of bare rock and encrusting coralline algae. This shift has a devastating cascade effect. The small, herbivorous fish that depend on the algae for food disappear. The complex hiding places provided by macroalgae vanish. The structural complexity of the reef declines, and the diversity of the entire community collapses. The urchin, once the humble guardian of the coral space, becomes the accidental architect of an ecological desert. The behavior of the urchin is governed by a deep-seated aversion to the light, a trait known as negative phototaxis. During the day, they remain wedged deep in the shadows, their metabolic rate ticking over at a low, energy-conserving hum. This is a survival strategy born of millions of years of avoiding visually hunting predators. Only when the safety of darkness falls do they venture out to feed. In some species, this need to hide has evolved into a bizarre behavior known as covering. Using their flexible tube feet, the same hydraulic appendages they use to walk, urchins will pick up fragments of shell, pebbles, dead algae, or human debris and pull them over their bodies. They effectively wear the reef as a cloak. This behavior serves multiple functions. It provides camouflage from predators above, offers a physical shield against the burning ultraviolet radiation of the sun in shallow water, and adds a layer of ballast that helps stabilize the animal in turbulent currents. The sea urchin does not possess a brain in the way we understand it. It lacks a centralized command center. Instead, its entire sensory and motor world is governed by a ring of nerves that circles the mouth, with branches extending into every spine and tube foot. This decentralized intelligence is perfectly suited for an organism that is essentially a sphere of defense. Every part of the urchin can react independently to a local stimulus, yet the whole animal can coordinate a retreat or a defensive pivot with seamless grace. As ectothermic animals, their metabolic rate is inextricably tied to the temperature of the water. In the warm, tropical shallows, their grazing activity and reproductive cycles are supercharged. They grow faster and eat more. But as the oceans experience unnatural human-driven heat waves, the urchin's resilience is put to the test. While they are famously hardy, extreme thermal stress can weaken their immune systems and disrupt their ability to maintain their rigid calcium carbonate tests, making them more susceptible to disease and predation. The continuity of the sea urchin's presence on the reef is ensured through a strategy of sheer reproductive volume. They are broadcast spawners, releasing massive clouds of gametes into the water column during synchronized events often triggered by the phase of moon or shifts in water temperature. The resulting larvae are microscopic, translucent drifters that join the great planktonic soup of the ocean. They may travel for hundreds of miles in the currents, a vast, invisible diaspora of defensive architecture. When a larva finally detects the chemical cues of a suitable reef, it undergoes a radical, violent metamorphosis. It settles onto the rock, its drifting, gelatinous form collapsing and rebuilding itself into a tiny, spiked globe. From that moment on, it is a resident of the stone. Within the broader narrative of the toxic food web, the sea urchin represents a form of environmental fortification. It is not an active hunter that seeks out conflict, nor is it a drifter that relies on chance. It is a benthic specialist that anchors its defense to the very floor of the ocean. The urchin does not need to be faster than its enemies. It simply needs to be more expensive to attack than it is worth to eat. It turns the reef into a landscape where every movement requires a calculation of risk. By radiating its canopy of spines, It declares its territory and enforces its boundaries through the sheer, unyielding logic of geometry and pain. As the night deepens and the currents whisper across the coral heads, the urchins continue their slow, methodical advance. They scrape the surfaces clean, moving grain by grain, needle by needle. The reef is a vibrant, chaotic tapestry of teeth and venom, but the urchin remains a fixed point of deterrence. It is a reminder that survival in the sea is not always about the chase or the strike. Sometimes, it is simply about building a better fortress and waiting for the world to realize that the stone has teeth. In its collective presence, the reef is modified, partitioned, and defended, a living terrain where chemistry and structure converge to redefine what it means to be untouchable. As the tide pulls back and we leave the silent, high-stakes world of the reef behind, remember that the most profound stories of our planet are often the ones hidden just beneath the surface, invisible, patient, and perfectly evolved. If you've enjoyed this deep dive into the ocean's hidden arsenals, make sure to hit that like button and subscribe to Earth's documentary. We are dedicated to bringing the world's most incredible ecosystems to your screen with the cinematic depth they deserve. Don't forget to ring the notification bell so you never miss a new exploration. From the smallest microscopic toxin to the greatest giants of blue, there's always more to uncover. Which of these masters of survival surprised you the most? Tell us in the comments below, and let us know which corner of the wild we should explore next. Until the next journey, stay curious and keep exploring the wonders of our world.